Good evening, all. You are joining the ATAL FDP organized by Oasis Institute of Technology, Tiruchirappalli, on the topic of quantum computing and AI, a potentially transformative synergy for future India. In today's session, we will be having a talk on quantum communication and quantum game theory by Dr. S. Balakrishnan, Associate Professor, Grade 1, School of Advanced Sciences, VIT Vellore, India. Dr. Balakrishnan has focused his research in advanced sciences with particular contributions to theoretical and applied physics. He has presented his research at various national and international forums and has guided students in exploring quantum applications. So over to Dr. Balakrishnan. Please get benefited, all the participants. Thank you for joining. Thank you.
Thanks a lot, sir. Thank you very much. So let me share the screen. So can you see the screen, sir?
Yeah, your screen is audible, sir, and also your voice is also audible. We can start, sir.
Can you see the next slide?
Yeah.
Okay, right. Fine. So thanks a lot. So it's my pleasure to be here to share some of the information related to quantum game theory and quantum communication. First and foremost, I must thank the organizers and also AACT for sponsoring this. I must thank organizers from Oasis Institute of Technology for providing me the opportunity to introduce this very interesting topic. The point is that over the days, you must have learned very many aspects of quantum computation, quantum information, and how it has been integrated into AI, though it is not fully done. But you could see the different facets of quantum computation. So today I'm going to introduce a very interesting topic, which is perhaps very rarely discussed in the research community because people have not ventured into it, though it has a lot of potential. So my objective of today's interaction with you is to introduce the subject called quantum game theory and how it is related, how it is relevant, and how it is fascinating. That's what I'm trying to do. And at the end of the session, perhaps you can have questions and I can also give you more details. Right. So with this brief introduction, let me proceed to the talk. So this is the brief outline of my presentation. So I will start with the preliminaries and what is game theory. When we say game theory, it is a classical game theory. So I will introduce some of the definitions and terminologies. Then we will dive into quantum version of game theory, and it's called quantum game theory. And we will discuss a very interesting but simple problem called penny flip problem. This observation was given by a scientist called D.A. Mayer. And then we study about quantum penny flip game and how it brings out the difference between a classical and quantum. Then we will discuss a very celebrated problem called the prisoner's dilemma game, which has been discussed by game theories for more than 100 years. So we will discuss about it in classical version as well as in quantum version. Then we will jump on to quantum communication. Then we will connect. We'll see the crossroads between quantum game theory and quantum communication. And towards the end, I will also highlight the significance of quantum game theory and what would be the future aspects of quantum game theory. And of course, I will also highlight in the context of quantum communication. At the end, I will also highlight some of the open problems prevailing in the field of quantum game theory and quantum communication. Right. So interesting point is, does nature play games? Yes, nature plays game. in both the sense, both macroscopic and the microscopic. At the macroscopic level, when I say macroscopic, whatever we can see by our naked eye, I call it as macroscopic. At a macroscopic level, all sort of competition is going on. It's not only the competition, but also cooperation also happens at various species. And there is an interesting concept called a selfish gene. So this concept is, of course, is known to us from uh, you know survival of the fittest. So we know very well we want to survive, and nature gives us such a intuition to survive, and we are doing it. So at a macroscopic level, everyone have this notion, and hence we have. So sometimes we compete with others, sometimes we cooperate with the others so that we can survive. So this is at the macroscopic level. At a microscopic level, also the same thing happens. There are very interesting papers published in the past in line with game theory, connection with the microscopic world. So I have given a couple of papers here which are well cited and which are path-breaking work in the sense of connecting microscopic world with the classical game theory. Right. So all this notion indicates something. So both at the macroscopic level, at the microscopic level, the phenomenon can be put in the framework of classical game. Right. So having said classical game, what is classical game? Who introduced that? So that's what we are going to understand. So a couple of gentlemen, Oscar Morgenstern and John von Neumann. Of course, John von Neumann was a mathematician. He contributed a lot in economics and physics also. They written a book in the year 1944, which is the foundational aspects of classical game theory. So then we have a very interesting gentleman. His name was John Nash. And there is a movie called A Beautiful Mind. I strongly recommend you to see this movie, acted by Russell Crowe as John Nash. So John Nash, a very interesting person. He had an issue, and but he brought out a very significant aspect in the case of a game theory, especially in economics. So three gentlemen over here in this picture you can see. Let me take the pointer. Okay. So you can see this gentleman, John Nash, and Richard Selton and Arendt. These three gentlemen were awarded Nobel Prize for their outstanding contribution in economics. And as a matter of fact, so for 12 Nobel laureates were working on classical game theory, they were awarded Nobel Prize. So it is a well-established domain. Classical game theory is a well-matured branch in mathematics. People has been extensively using it in various domains. So not only in mathematics, but also in economics, political science, marketing, finance, and so on and so forth. So it's a well-known subject. Right. So basically, what is a game and how we define it technically? Right. So here you can see game consists of set of players first and foremost. It can be individual player or a group of players with different teams or two teams, and a set of rules that dictate what the players trying to reach. It can be a money, or it can be a name, or it can be a reputation, or it can be a profit. It can be anything for that matter. So for which the players are working on. So the players play against each other, and then they try to win the game. Right. So as I said, the player can be, as a human, or even a DNA for that matter, or any species for that matter. So it can be an individual or set of individuals. Right. What do you mean by payoff? So payoff is a technical term which is always a real number associated with outcome. So usually we denote the payoff by the dollar symbol. Though we say it is in terms of money, the reward can be in terms of other way also. Right. We will see as we proceed further. Right. The move is nothing but what are the possible action and choices available to the player. Right. So when I say possible action or choice, I give you an example. You assume that you know how to play a chess game. right? You know the rule of the game, right? So we play the game alternatively by moving the coins, right? So you know the choices and actions available to you, right? So having given what you're going to play, that makes a difference. That is called, strategy, right? You know the set of rules and what you're going to make a move. What is you're going to uh, uh, bring it into the ground. That is what we call it as strategy. So strategy of two types: pure strategy and mixed strategy. So when you say pure strategy, you decide and go ahead. No, that it with certainty. You don't have any second opinion. You don't have any ambiguity about your strategy. Right. What do you mean by mixed strategy? Sometimes, you're not sure what is the decision you have to take. Then we do some, informal way of taking decision, right? For example, tossing a coin, right? You want to decide something and you toss a coin. So head means you want to do, tail means you don't want to do, right? But it is absolutely a probabilistic one, right? And so tossing a coin is absolutely a probabilistic one. And when we make a strategy based on that, then you call it as a mixed strategy, right? What do you mean by dominant strategy? So dominant strategy is the one gives you higher payoff than any other alternate strategy. So that you always try to apply. So if you know that if you do it again and again, you will get the benefit, you will get the reward, then we always try to do that. We never want to lose it. So it is called dominant strategy, right? What is Nash equilibrium? This is the point where our John Nash come into picture, and he gave a very interesting equilibrium. It's called Nash equilibrium. So any classical problem, we try to look for Nash equilibrium. Why it is so? Because of the following reason, right? What do you mean by Nash equilibrium? It is a set of strategies from which unilateral deviation of a player reduces his or her payoff, right? So what do you mean by that? So I stick on at a particular strategy, right? If I try to deviate, then what will happen? I will be losing. I will be getting rid of my payoff, right? My reward will be reduced. So this is the definition of Nash equilibrium. So any deviation from this particular strategy is not suitable at all. Such a point is called Nash equilibrium. So we try to achieve Nash equilibrium in the game, and we want to stick on with that. Right. The converse to Nash equilibrium, which is more powerful solution, is called a Pareto optimum. It's called a Pareto optimum. What do you mean by that? It means that there are no other solution in which all the players simultaneously do better, right? It's a kind of a cooperation. All the players want to have the same kind of payoff. They want to reach the same amount of profit, right? Then they have to look for a solution, not as a Nash equilibrium, but for a Pareto optimal. So Nash equilibrium and Pareto optimal are kind of a competing process. Sometimes we see Nash equilibrium and Pareto optimal one and the same. Some game type, these two are different, right? So what do you mean by information? So information is something like this. So when I make a step, my opponent know what I'm taking a step. So for example, you play a chess game, right? When my opponent makes a move, I am aware of it, right? With what notion he makes that move, I don't know, but I know what is the step he makes. On the other hand, for example, there is a auction or a closed auction, then people may not know what is the amount was bidding, right? So there is a closed information. So we don't know the information completely. So the games also has some information, full information, or otherwise known as complete information or incomplete information, right? There are further classification of games. It's called the symmetric. When you say symmetric, both the players have the same choice and the same outcome associated with that. There is no partiality in the game, right? The game structure is like that. It's called a symmetric game. And sequential game is something like the players are making the steps on a sequential way, like a chess game, right? Playing one after another. Carom board is another example for a sequential game, right? What is a simultaneous game? All the players act at the same time, right? So then you say it is a simultaneous game, right? Rock, paper, scissors, a very, very simple game played by children comes under this category, right? Zero sum game is nothing but sum of all the payoff is equal to 0. So for example, when two players zero sum game is also called duel. So what do you mean by that? Let us take a cricket match 2020, right? So one team wins, another team loses. So one player's win happens at the cost of other player's loss. So it is called a zero sum game, right? The other extreme scenario is non-zero sum game, wherein players' total sum is not zero. It is something like in a partnership game. So 2 or 3 people come together, put an investment, something like 30% and 70%, and there is a profit. Accordingly, they take the profit. If there is a loss, accordingly they divide the loss. So here, if you add the sum, it is not zero, since it is called non-zero sum game. So usually market or stock market comes under the category of non-zero sum game. Right. Having said this, now let me introduce some of the technical aspects, which is very much necessary as we proceed into the slides. Right. So when I say simultaneous move, both the players, let us say, for the simplicity, I'm taking 2-player game. Right. So when both the players take the steps simultaneously, then it is called simultaneous game. Right. So there are some matrix form. It is called payoff matrix. Called the payoff matrix. So payoff matrix is crucial to decide what is the benefit the players are getting. So when you say symmetric game, you can see the matrix over here. It's basically symmetric matrix. What do you mean by symmetric matrix? Row becomes column, column becomes row. You can see here xy becomes xy, row becomes column, and wz becomes wz. So this is nothing but in the language of mathematics, this is nothing but a symmetric matrix. So this matrix is called payoff matrix. Every classical game has a payoff matrix. And when the payoff matrix assumes a particular form, then we classify them accordingly. So in this game, you can see here, it's a symmetric game. So symmetric game has this particular structure, right? So when you come to so-called potential game, the potential game, you have the x, y, y, z, all the entries are the same. And you can see zero-sum game. When you have zero-sum game, all the entries are negative. You can see x minus x, y minus y, and w minus w, z minus z. When you sum it up, the total sum becomes 0. It becomes a null matrix, right? So you can see the examples corresponding to each and every type of game. So symmetric game, so prisoner's dilemma, we will see the exact description later. And potential game, it is nothing but partnership game. It is nothing but in the business model, people come up with the partnerships, right? That is described by this. And when you have this type of game, when you have this type of game, potential game, you have the business model. And zero-sum game, predominantly, 2 players or 2 teams. One team wins at the cost of the other. As I pointed out, you take a cricket match, which is a very typical example, and you can take a chess game. So all those games come under the zero-sum game, right? The other extreme class is sequential game, where players make steps one after another, right? Chess game, tic-tac. So these are all come under the sequential game. So people move in a sequential way. So this is something like a tree kind of thing, decision tree, right? So decision tree is coming up, and accordingly players take a step. Okay, so if I make this move, what will happen? If I make this move, what will happen? If my opponent makes this move, what will happen? Accordingly, they take a decision. So that is a reason why chess game is considered to be very difficult. Why it is considered to be difficult? Because I should make a step, I should make a move, and I should also guess if I make this move, what my opponent will make, right? So it is a kind of a backward induction problem. So I should know what he will react if I make this move. So that is the reason why chess game is not so simple and easy, right? But chess game comes under sequential game type. Right. Some applications of classical game theory, which has been shown in the recent times. So one of the recent papers is highlighted here. Um, sorry. So it is a paper in Nature Communication, which talks about how genes divide themselves and then form the pair. Right. This forms a table. This forms a table which is very much like the payoff table what we witness in the classical scenario. Right. So the genome driven evolutionary game is very much interesting one, and people have given lot and lot of interpretation for this. Right. So basically, nature prefers to exist in an equilibrium, which is very much like a Nash equilibrium. Right. So what do you mean by Nash equilibrium? So when you deviate from that particular strategy, then you'll be losing. Right. So nature never want to lose the existence of certain species. Of course, it has to be extended to the other species as well. So in general, there is a pattern being observed, and the pattern is very much relevant to the payoff matrix, and nature tries to achieve a Nash equilibrium. So this is one example I would like to connect with, biology, classical game theory and biology. Right. So genotype and all, that's what is explained over here. And another interesting experiment was performed. It is with the pair of chimpanzee. It's a very interesting game, and it is called symmetric match penny scale. And so basically, we have two chimpanzee, and they have two different buttons, two different colored buttons. They have to press the button. Okay, so there is a communication between them after some time. It's not happening immediately. After some time, they generate some sort of a communication. They start to attain a path. So initially, they randomly pick the buttons, but after some time, they start to find some sort of a correlation. So this experimental setup indeed prove that there is a communication between two chimpanzee in a way so that they can maximize their winning probability. So what is the winning probability here? When both the chimpanzee press the same button, then it is considered to be a winning. Right. So initially random pick, after some time they learn and then they reach the winning. So this is another interesting experiment performed by scientists in line with classical games. Right, chimpanzees makes competitive decision that align with prediction from game theory. Right. So as I mentioned, after long trial, what will happen? Both the chimpanzee press the same button as per the prediction of game theory, and it happens to be the Nash equilibrium. Right. So let us play this game. Very interesting one. Of course, there are a lot of online tools are also available to play this game. Okay. So let us start to play this game. It is nothing but a classical penny flip. So consider a person called Bob. So Bob wants to play this game. So rule of the game is something like this. We have a fair coin. So this coin has either head or tail. Right. We have only one coin, but it's a fair coin in the sense that we can show either head or tail. Right. So the initial state is either head or tail. Right. So we have a person called arbiter. So arbiter is something like a judge. Okay, judge is holding the coin and he is holding a fair coin and informing to the participants. There are two participants in this game. One is Bob, the other person is Alice. Right. So the game goes something like this. So Bob will ask the judge to flip the coin. So for example, if the initial state of the coin is head means, then Bob will ask the arbiter to change the head state to tail state. So this is the choice. So it is called flipping. Or Bob can also retain the coin in the same state, meaning head in the same state head. Right. After that, the second player called Alice, she starts playing the game without knowing. Of course, whatever strategy adopted by Bob is not known to Alice. So Alice also has the same choice. So she can inform to the judge whether to retain the state of the coin or to flip. So once again, when we say flip, it is nothing but we can retain in the same state ahead, or it can be to tail. So this is the scenario. Now, once again, Bob get a chance whether to retain the coin in the same state or to flip it. So this is how the game goes, right? So can you tell me the type of this game? Is it a sequential game or simultaneous game? Any participant can respond. So players are playing one after another. So what is the class of game? This simultaneous or sequential?
Sequential.
Sequential.
It's a sequential game. Very simple. But so now this is how the round goes. Now, what is the rule? The rule is something like this. If the initial state of the coin is same as the final state after this round is the same, then Bob is declared as a winner. Bob is declared as a winner. Otherwise, Alice wins. Right? So I hope you understand. So we are so-called the judge start the game with the state of the coin as either head or tail. Then Bob can retain the state of the coin in the same state, or he can flip it. Then Alice gets a chance. Alice, of course, does not know what Bob has done, and she can either retain the coin in the same state or she can flip it. Then it goes to Bob. Of course, Bob does not know what Alice has done, and once again, Bob perform either flipping or no flipping. So after that, the judge tells what is the state of the coin. If the final state of the coin is same as the initial state of the coin, then Bob is declared as a winner. Otherwise, Alice is declared as a winner. This is the game, right? So can you tell me who can win the game? Alice or Bob?
Bob, sir.
Bob. Okay. Naturally, we tend to think so because Bob is getting two chance to play, right? Two chance to play. But interesting to see that both the players have equal probability of winning the game. Right here, we have the table, exhaustive list. Okay, Bob's move, Alice move, Bob's move. Whatever combination you take, at the end of the day, the winning probability for Alice and Bob is 50-50. Right? This is the classical scenario. This is called classical penny flip. There are some links are available wherein we can play the game. Okay, you can start the initial state as something like head, then you can apply these moves, then you can see the result. Right? If you play the game again and again at the long trials, you will see that both the players have equal probability of winning. Right? So this is a classical scenario. Right? Now we can play the same game in quantum version. Right? What is the quantum version? Right. By this time, I hope you know what is the so-called this notations. This is something like spin. Okay, spin of a particle. Let us take an electron. Electron is a spin half particle. It can show either spin up or spin down when you apply a magnetic field. So it's this arrow indicates spin up, this is spin down, and this notation is called a Dirac notation. Okay, so I don't want to get into the detail. So it is nothing but something like a coin. But the difference is that this coin can exist in a superposition state. What do you mean by superposition state? When you have a classical coin, at a time, it can be either head or it can be tail. But if you have the same coin in the microscopic level, it can be a combination of head and tail. Right, that is what is being described here. So when you have an electron, if you don't apply any field, magnetic field, the electron will be oriented in all possible directions, which can be represented as a sum of spin up and spin down. But when you apply a field, what will happen? The electron will show either spin up or spin down. Right. So this is the coin now. So in the microscopic world, we are playing this penny flip game using a particle, so-called electron. Right. Rule of the game remains the same. So now our friend Bob, who is known as quantum player, he applies an operator called head mod operator. Right. So what is header mode operator? I will come to that. So after this operation is imposed on the coin, Alice remains as a classical player. Right. What do you mean by that? Alice can either flip or can retain in the same state. So the state of the particle can be retained either in the spin up state or spin down state. Right. Now, once again, Bob gets the chance, and once again, he applies header mode. Right. And the final state is head or tail. Now, the point is, whatever be the state of Alice, Bob always wins the game. Right. This is the quantum mess. Right. Understand the difference? When you play this game, penny flip game, though Bob gets 2 chances, Alice gets only 1 chance, both the players have equal probability of winning. But when you play the same game in the microscopic world, all the time quantum player who applies an operator called header mod wins against the classical player called Alice. Right. So how it works? Very simple. You can a small math is introduced so that you can appreciate it. Right. So what you have, this is the header mod operator. And when header mod operator, this is a matrix form. It's basically a single qubit operator. It has a matrix form. So what happens when you have this get 0 is nothing but your spin up state. So it is a spin up state. So a spin up state is designated as get 0. Right. So in the classical computation, we say no binary zeros and ones. Correspondingly, we have get 0 and get 1. Right. So what is the action of this header mod operator? This header mod operator actually creates the equal superposition. Creates an equal superposition. So now what happens? Alice has only 2 chances, right? Either she can use flipping or no flipping. So when she applies no flips, what will happen? It remains the same. The state of the coin in the superposition state remains the same. It is denoted as get plus. When she flips, what will happen? Once again, you can see 0, get, it becomes get 1 plus get 0. Right. So this is the state after flipping, but it makes no difference, right? 0 plus 1 or 1 plus 0 doesn't make any difference. Right. Now what happens here in final step? Once again, Bob applies header mod operator. You can do simple matrix multiplication. At the end, you can show that the initial state is get 0. The starting state is also get 0. So if you start the game, something like get 0 as head. So after the end of the game, Bob retains the state as head. If you start the game with the tail, which is designated as get 1, then it's possible for Bob to retain in the same state. So now what is the message? The message is that the one who applies quantum strategy called header mod operator wins the classical player. Wins the classical player. Right. So this is what is given. Note that even if you try to apply in a much more extended space for Alice, still Bob can win the game. Still Bob can win the game. As long as Bob is applying header mod gate, which creates the equal superposition, can always win the classical opponent Alice. Right. Now let us have a quick question. If Alice is also happen to be a quantum player, what will happen in the game? Just to summarize, when you have a classical game, both Alice and Bob adopts classical strategy, flipping or no flipping. Then what is the success probability? 50-50 chance. Right. In the quantum world, when you play this game, and we have a quantum player, Bob is a quantum player, and Alice is a classical player. Right. Then all the time quantum player Bob wins. And now you can extend this problem further. Alice is also given a freedom to use quantum strategy. So both the players are quantum players. Then what would be the scenario of this game? What do you expect?
Both of them may be winner.
Both of them not maybe the winner. 50-50 chance to win the game. Okay. Which is very much like the classical game. right? In the classical players, both of them are classical players, then 50-50 chance. When both of them are quantum players, then 50-50 chance. If one is playing quantum, other one is playing classical, then quantum player takes the advantage, right? This is the moral of the story. And in fact, this work is published in the very reputed journal in physics, and it is known as Physical Review, right? PRL. And David Mayer, he introduced this particular work, and he titled this paper as Quantum Strategy. Note that his intention was to introduce quantum algorithms. So when you want to conceive any quantum algorithm, it can be thought of a quantum game. It can be thought of a quantum game. That's how the field of quantum game theory started to evolve. Okay. So this was the very first paper which shows that quantum player can take the advantage by moving or by using quantum strategy called head-mod operator. Right. So this is the starting point. And what is the application on the whole of quantum game theory? Because we want to write algorithms. So we want to write quantum algorithms. We want to make a comparison with the classical algorithm. Right. So what is the simple message given by David Mayer? When you apply quantum strategy against the classical player, then you can take the advantage. So this is the main outcome of this paper, and this was the starting point. Right. Using this very well-known classical game called the Prisoner's Dilemma game, which is celebrated one because it has been discussed in the history for more than 100 years. People try to solve this game. Right. It's a very simple to explain. So assume that once again there are two players, Alice and Bob. They were together and they were arrested by the police. With a, it seems that they have involved in a crime scene. So the police interrogating them without making any communication. So Alice and Bob are undergoing this interrogation without knowing each other. Okay. So now this is the payoff matrix. How we generate this? So it's basically a reward. 3 is nothing but a reward. I will tell you what I mean by reward and all. So then punishment is 1. Okay. So what are the choice? So either they have to confess the crime or they have to deny the crime. Okay. Either they have to confess the crime or they have to deny the crime. Right. What are the possibilities they have? So Alice can say that, yes, I did. That is one possibility. The other possibility, Alice can say, no, I have not done, but Bob did. Right. Same is the case for Bob. Right. Bob can say, no, I did not do, but Alice did. Right. So that is the reason why there are these options are coming up. So reward. Okay. So reward is 3 and 3 in terms of, kind of punishment. Right. And punishment is nothing but in terms of jail period. Okay. For example, reward, when you say 3 years in jail, right? Punishment is 1 year in jail because they don't have a proof. Temptation. What do you mean by temptation? Bob is tempted to say that become a witness instead of become a suspect. He becomes a witness for Alice crime, and the same is the case for Bob, right? And that's the reason why we have temptation. So kind of the investigation officer saying to Alice, no, Bob has informed that you have done. Now you confess your mistake, like that. Okay, so this is the possible scenario. Right now, what happens? The rational thinking tells to the players, Alice and Bob, to deny their crime. Okay, whether they involved or not, they want to deny. Okay, so this is something like a Nash equilibrium, right? Why? So this is common sense, right? This is common sense to deny at a first instance. So this is a Nash equilibrium. But what is interesting point is 3,3 is the Pareto optimal. When they confess, they can say it's 3,3. In this case, I can put -3, -3 also. They spend less time in the jail. Why? Because they confess the mistake, right? They have not denied, rather they confess the mistake, right? So we can even say -3, -3. Minus sign indicates that less time in the jail, right? So now there are 2 points here. One is the common sense tells to the players that at a first instance to deny, which is the Nash equilibrium. But ideally, they want to spend less time in the jail, which is the Pareto optimal. So this is the dilemma. This is the dilemma of the game. Note the point, Alice does not know what Bob said. Similarly, Bob does not know what Alice said. Okay. So collectively, if they want to cooperate, then what they want to do, they are supposed to spend less time in the jail, which is what is desired. But what will happen? The common sense tells that denying at a first instance. So confessing is something like gives them less number of years in the jail when compared to denying. Right. So there is a conflict. There is a dilemma whether to choose confessing or denying. So this is the problem. This is the whole uh, whole aspect of prisoner's dilemma. Right. This game is extended to quantum version, and whether Alice and Bob come out of this dilemma, whether they spend less time in the prison. That is the question when they play this game in the quantum domain. Okay, so what is the one-to-one correspondence? The one-to-one correspondence is given here. So in the case of classical game, we have so-called bits. In the case of quantum, we have qubits. So here the correlation only through rational expectation, right? And when you say, okay, so Alice is guessing, okay, Bob would have said this. Similarly, Alice would guess that, okay, Bob would have said this, and vice versa. Whereas here, what happens, there is an interesting scenario that is nothing but entanglement. So entanglement come into picture and it is going to save them, right? And I hope you people are aware of entanglement and its characteristics, right? So any idea about entanglement, or should I give any brief note? So entanglement is a non-local correlation between the particles. Okay, when you say two particles, let us take two electrons, when they together, they develop some sort of an interaction. And when you separate them spatially, whatever be the distance, they retain their correlation. Right, this aspect is called entanglement. So entanglement is a resource. So entanglement is a resource. We say energy is a resource, right? So energy is a resource, and energy can be neither created nor destroyed. Same is the case. Entanglement is a resource for useful information and computational tasks, quantum information and computational tasks. Right. So this case, in the case of classical scenario, we read the message, we read the outcome readily. But in the case of quantum, we have to make a measurement so that the superposition is collapsed. Right. You might ask the question, sir, what is the connection between superposition and entanglement? So entanglement is nothing but high degree of superposition. Nothing more, nothing less. In a very layman's way, we can say that entanglement is a very high degree of superposition. Right. So now the point is, the classical prisoner's dilemma game, we are going to play in the quantum version. So for that, we are going to adopt a technique. Okay. So here, as I pointed out, we have so-called bits is replaced by qubits, and the player strategies are adopted by unitary operators. Finally, the payoffs are measured, and we follow it in a particular sequence, and it is called EWL scheme, Einstein, Wilkinson, Levenstein scheme. So this is the very first proposal to quantize classical game. Right? This is a very formal framework using which any classical game can be quantized. So EWL, so Isert, Wilkinson, Levenstein first quantized prisoner's dilemma, and then they have showed the power of the game. Right. So here you can see the here you can see the circuit. Right. It's nothing but a quantum circuit. It's not simple circuit. It's a quantum circuit. Right. Moment you have a quantum circuit, you always we have to think of logic, quantum logic. So this is a quantum logic. So we have initial state and the operator, and UA and UB are the strategies adopted by Alice and Bob. and J and J dagger creates entanglement. So note that initially the two particles, they don't have any connection, and this operator J, it's called entangling operator, which creates entanglement between these two particles. Then these two particles are shared with our friend Alice and Bob. Then they are adopting their strategy. This is the strategy available to Alice and Bob. Then once again, so-called arbiter or the police, they apply operator. It's called disentangling operator. And finally, they make a measurement. Right. This is the framework using which the classical game is quantized. Right. So note that it is a circuit implementation. It's a quantum circuit. It can be implemented. Right. So now when we play this game, the same thing. Or whatever we say for the classical, it's also being shared in the case of quantum mass also. But the basic difference is that this is the operator. This J is the operator, which creates entanglement, which is not the case in the classical game. Okay, so the entangling operator is the one which decides the power of quantum mass. Okay, so average payoff is calculated. Okay, little more mathematics come into picture. I don't want to discuss more on that. Okay, so now this is the graph. Okay, so basically what we have done, we have computed the average payoff. You can see here dollar symbol. You can see the dollar symbol here. So this indicates what is the payoff obtained by Alice and Bob after playing this game. Maybe n attempts. So it is a kind of a n trials. Then we got this expression. So this expression, all the values are plugged in, and once you do that, you will get the expression. So there you can substitute the very first scenario, namely, very simple case. Then gamma is 0. What do you mean by gamma? Gamma is nothing but entangling parameter. So entangling operator parameterized by gamma, which happens to be 0, means there is no difference at all. It is nothing but a simple classical game. So this game is nothing but a classical game. So why it is so? Because there is no quantumness involved, right? So still pareto-optimal, still Nash equilibria exist independently, and hence dilemma exists because it is a classical game, right? And now when you apply so-called maximally entangled state given by this parameter gamma equal to pi by 2, in the expression you have to substitute that. Then you got a new expression. It's nothing but 3,3. This is the value we want, right? In fact, I can, as I pointed out, I can put -3 also for a particular strategy called Q, Q. So when Alice and Bob play the quantum strategy called Q, Q, when there exists an entanglement between the particle, then they can reach the pareto-optimal. So Nash equilibria and pareto-optimal coincides each other. So there exists no dilemma at all. So Alice and Bob happily come out of the situation. They spend least year in the prison because they are adopting quantum strategies, right? So this 100-year-old celebrated prisoner's dilemma problem, when you play the game in the microscopic world, then there exists no dilemma at all. So this indicates the fact that quantizing the classical game is useful. Not only that, why it is not only that, players should also empowered to use quantum strategy. Q, Q is a quantum strategy. Okay, so what is Q, Q? This is the Q, Q. So I 0, 0 minus I. So it is nothing but a Q strategy. When they apply, they can resolve this, provided the entanglement should be maximum. Right. So we have a scale, we have a degree of entanglement. Right. When you say 0, gamma equal to 0, which is nothing but a product state, and when you say gamma equal to pi by 2, maximally entangled state. Anything in between these two, it's called a non-maximally entangled state. But non-maximally entangled state does not bring any advantage. Only maximally entangled state brings the advantage. So that is the beauty of this particular problem, right? So now one can say, what if one player uses quantum strategy, other player uses only classical, right? When this sort of a thing comes, what happens? There exists a miracle move which benefits the quantum player. Okay, if Alice uses quantum strategy and Bob Alice used quantum strategy, advised to play this move. It's called a miracle move, and all the time he can escape. Sorry, she can escape. Alice can escape because she is playing quantum strategy, whereas Alice is adopting only classical strategy. So, sorry to say again, Alice uses quantum strategy and Bob is using classical strategy. And since Alice is using classical strategy and she is a quantum player, so quantum player gets the maximum benefit, meaning to say, Alice comes out of jail with the minimum imprisonment years when compared to Bob, right? So this once again, this corollary analysis indicate the fact that quantum players always benefit. And when both of them play the quantum strategy, then both of them will be benefited out of this. Okay, so note that Alice and Bob cooperate each other and they adopt the same strategy called the Q strategy, and hence they succeed. They come out of the dilemma. So Nash equilibrium and Pareto optimal becomes the same, and there exists no dilemma at all. And when you consider the next scenario wherein Alice is a quantum player and Bob is a classical player, then all the time Alice is safeguarded by the quantum strategy, right? So far I have given you the story of game theory and quantum game theory. Now let us move on to the other domain, which is nothing but communication, right? You can see all those pictures here, right? So Bob and Alice, they are spatially separated. They want to convey the message through some means, right? What are the possible options they have to convey the message? They can send by message, text message, telegram, WhatsApp, right, through email, and so on and so forth, right? So the information is sent by a sender and to a receiver by means of some medium. Okay, when we say medium, it can be free space medium, something like a satellite communication, or medium based communication, something like optical fiber. So for example, you take LAN network, right, local area network wherein fiber is used, and then that is nothing but medium, right? So this is the classical scenario. In the case of classical scenario, there is a process called encoding and decoding. So for example, these are the messages on the right hand side: hello, goodbye, yes, no. These are the messages Alice wants to convey, and she encoded this message into these bits, zeros and ones. So 00 means hello. 01 means goodbye. 10 means yes. 11 means no. Right. So there is an encoding process by means of a color, and when this message is passed on to Bob, and Bob has to decode it. Right? How does he work? He decodes again by means of color, and for instance, blue color means it is 00. That gives a message something like hello, right? So this binary encoding and decoding is a very simplest technique, so that we can try to escape out of eavesdropper. But the scenario is not like that, right? Whenever Alice and Bob communicate through any classical channel, right, and so-called eavesdropper Eve sits in the line and he always attacks. So meaning to say, if Eve is always sitting, hiding himself in the communication line between Alice and Bob, after some time, Eve can start to extract the message from Alice to Bob or Bob to Alice. So all these classical communications are under threat by eavesdropping. So it is not a secure, the communication channel, classical communication channel is not secure, right? When you play this game in the quantum domain, you call it as quantum communication. So what you do here, so here you play the game in a different way. And how do you play the game? So here you're having the qubits, and you are once again doing the encoding and decoding by means of some encoding rules, and then you are transmitting. You're transmitting through the quantum channel. Once again, optical fiber I can say, but this time we are sending a photons one by one. I call it as photonic qubit. And this is reached. So Alice is preparing the message and encode it and passed on the particles, photons, let us say, to Bob. And Bob is receiving it. And then note the point, Alice can inform the so-called encoding rule through a classical channel. Publicly, Alice can inform what is the encoding rule. Why it is so? Because two facts. One is particles has reached Bob's side. The second one is Eve cannot do. Why Eve cannot do? Because there is a very strong concept called no cloning theorem. So no cloning theorem tells you that the unknown quantum state cannot be copied. So for Eve, all these qubits are unknown. What do you mean by unknown? Unless Eve makes a measurement, she does not know what is the state. If she makes a measurement, what will happen? It will collapse. The state of the particle will collapse. So that will indicate the presence of Eve to Alice and Bob. So because of no cloning theorem, quantum channels are secured enough and the communicant can exchange the message without any fear. Right. So when you have classical things, there are certain difficulty. When you have quantumness, there are very many advantages. The first thing is impossible to copy an unknown quantum state. It is a continuous one, superpositional state. So it means you can accommodate more information when compared to the classical one. And most importantly, it can be entangled state also. And since it is not known, the qubits are not known, it cannot be perfectly distinguished. Meaning to say, one cannot perfectly say whether it is zero state or one state in a classical sense. Right? Not possible to delete one copy against the other by any physical means. It means no deletion. So the two aspects are crucial. One is called no cloning. It means unknown state cannot be copied. The second one is no deletion. The unknown quantum state cannot be deleted. These two are the powers given by so-called quantum mechanics to quantum communication. Right. So when you have quantum communication, there are certain historical development. I just want to indicate them. The first aspect is called quantum key distribution. So you must have heard from other speakers over these days. Quantum key distribution was the very first breakthrough happened in the quantum communication. Right. So what is this all about? So in this case, you have Alice and Bob produce a key in advance. It is basically a secret key they develop. And then after that, they separate each other. So basically, they produce a secret key in advance when they are together, and then they keep a copy of it, and then they make use of it for the encryption and decryption process, encoding and decoding process. So this is the very first concept come into picture in quantum communication. But what is the drawback? There are drawbacks because when you want to have quantum key distribution, both Alice and Bob should be in the same place. They should be together to generate the key, which is highly unlikely, right? So then we have so-called improved quantum key distribution. It is called quantum key agreement. Both the parties utilize the same quantum key. Okay. Once again, it is the same point, but it is an improvised version. But still, the solution is not reached. Right. Then we have QSS. It's called quantum secret sharing. So it's a very interesting one. So there are n parties, okay, n participant, and they are sharing a message, and it is distributed across all of them, and all of them should cooperate. All of them should cooperate in the sense that all of them should tell what is the initial state with which the state is prepared, quantum state is prepared. Then only it is possible to read the message. So if any one of them is trying to cheat the others, they cannot read the message at all. It's called quantum secret sharing. The next development happened in the name of quantum secure direct communication. It's a direct communication Alice and Bob directly they can do, and then they can do it without generating the secret key first. This is the breakthrough work next to quantum key distribution. So in the case of quantum key distribution, both the parties together, and then they generate the entangled state, and then once they space apart, they make use of the entangled state for the communication. But the drawback of the scheme is that The participants supposed to be together in the same place to generate the key, right? But in the case of quantum secure direct communication, there is no such a requirement. Alice and Bob start to communicate directly using entangled state generated by one side, right? Then note that another interesting development happened. It's called quantum bidirectional direct communication. What do you mean by bidirectional? Both Alice and Bob, they can securely send a message. Both Alice and Bob. It's not a one-way communication, rather it's a two-way communication. So most important characteristic is that it's, in a general sense, it's called quantum dialogue. Right? What do you mean by dialogue? Both the parties supposed to exchange their information, right? Then you say it is a dialogue. So here it's, in a generic sense, it's called quantum dialogue, right? The very first quantum dialogue was proposed by the set of authors, and it is well cited work, and that I just want to describe it so that you can understand this. Basically, it's called controller dependent protocol. So we have two parties, Alice and Bob. They want to exchange the information, but there is a person called Charlie. So he is a middleman. He's a middleman. He's a controller. Right? What he does, he prepares an entangled state. There are four possible entangled states. It's called Bell states or maximally entangled state. So Charlie basically prepares any one of them, and one is given to Alice, another one is given to Bob, and then they are doing all the encoding and decoding rule as per the very classical sense. Then they are doing security checking and all. After that, they exchange the particles. Okay. So encoding happens, decoding happens at both the sides. So it's a bidirectional communication, but still Alice and Bob cannot read the message unless Charlie tells what is the initial state. What is the initial state? Okay. So this is called Chang's protocol, and this is a controller dependent protocol. So what is the drawback? Alice and Bob exchange the information only under the supervision of Charlie. Right. There are some drawbacks. Basically, Alice and Bob, just like that, cannot exchange information because they strongly depend on Charlie. That is one thing. The other aspect is, if Charlie is a malicious person, in the sense he is trying to cheat either Alice and Bob, then Charlie can give incorrect information to one of them, and hence it is not a proper communication. So it is not a secure communication as well. So these are all the drawbacks of controller dependent protocol, and hence there is a technique, and it is introduced. It is called controller independent protocol. Right? What is this all about? Once again, we have Alice and Bob, but there is no Charlie. There is no controller in this case. Instead, Alice has every power to generate entangled state. Now Alice has the provision to create entangled state, and she creates any one of the initial state. Initial Bell state, of course. So then it is shared with Bob. So Bob is using the message, his message. Alice is also using his message. Then after that, they are exchanging the encoded thing. Then they can read the message without any difficulty. So it's a well-written protocol which helps to get rid of so-called the controller. And also it gets rid of the issue of security, right? If Charlie is not a secure person who is trying to cheat, then the communication is not proper. Since Charlie is not present in this protocol, there is no worry about the security level. So this is the basic idea of controller independent protocol, right? So then this problem is something like this. So here in this protocol, it is used maximally entangled state. Note that generating maximally entangled state is not so simple. Physically, it is very difficult, and it is also very hard. And maintaining entangled state for a longer time without decoherence is also physically challenging. Right? Considering all these facts, the question come out: can we do controller independent protocol using non-maximally entangled state? Then the answer came out to be yes, but the point is there is a lower threshold value. There is a threshold value. You can't do without any entanglement. You need to have entanglement, but it need not to be maximally entangled state. So how does it work? It works on the very simple logic. So Alice prepares the entangled state with a particular degree of entanglement, Okay. And Bob is also doing the same thing, and they are making a comparison. They making a comparison between the entangled state generated by Alice and the Bob. Right. If the same degree of entanglement is generated by the proper understanding, then Alice and Bob can exchange the message using non-maximally entangled state. Here, the interesting point is that eavesdropper cannot do anything for two reasons. The first thing is that eavesdropper does not know what is the bell-neck state is used. The second one is what is the degree of entanglement is being used. When we say degree of entanglement, it is greater than 0, less than. So when you say degree of entanglement is 0, then it is nothing but a classical scenario. There is no entanglement at all. When you say degree of entanglement is 1, it means it's maximally entangled state. When you have any value between 0 and 1, it's called non-maximally entangled state. So it can be any value, for example, 0.4, 0.7, 0.8, right? So Alice can prepare an entangled state with a degree something like 0.7. Bob can prepare a entangled state with a degree something like 0.7. If these two are matching, then they continue the information, they exchange the information. And since with what degree of entanglement being prepared by Alice and Bob, eavesdropper cannot steal the message. So it's a secured one. So it is possible to achieve controller independent protocol using non-maximally entangled state. Right. So now a lot of other protocols, quantum communication protocols are popping up using cluster states also. So here you can see it's a 6 qubit. You can see here A1, A2, B1, B2, and C1, C2. These are all kind of qubits given possessed by Alice, B1, B2 possessed by Bob, C1 and C2 possessed by Charlie. Right. Once again, it is a 6 qubit protocol using controller, Charlie as a controller. Right. So if you look at the scenario, once again, the same process happens, and they depend on Charlie's declaration. So Charlie is supposed to tell what is the initial state with which the 6 qubit entangled state is being preferred. Based on that, Alice and Bob can exchange the information and then they can read. Right. But if you ask me what is the advantage, as number of qubits increases, we can keep more message. That is the one thing. But practically, how to implement, that is always a question mark. Right. So here, there is a very interesting concept. It's called the first mover advantage. Once again, I switch over to game theory to make a connection. Right. So there is a game called Stackelberg duopoly. So when you say duopoly, it is it's a two-player game, or two company or two market. Okay. So they play the game, and it's a particular way of playing. It's called a Stackelberg. And what do you mean by Stackelberg? So here they see in a market, there are two things that are important. One is what is the quantity and what is the price, right? So if you produce more quantity, naturally the price will be less, right? That's the idea. And if you have a less quantity and demand will be more, so price will be more. So which one you are going to vary, quantity or the price? So that is the question. So based on that, there's a class of game called Stackelberg duopoly game. And here there is always the first mover gets an advantage, right? Even in the chess, people always believe that the one who uses the white pawn first, right? White coin first, they have an advantage. So first mover always takes an advantage, right? So similarly, there is an advantage realized in the communication protocol also. Okay, so this is a kind of a one-to-one correspondence between quantum game theory and quantum communication. It is not an all scenario. It is a particular scenario. It's a Stackelberg game. It's a 6 qubit protocol one side. As I described, you have 3 parties they are communicating, and in the Stackelberg we have company firm A, firm B, and there is an arbiter. Right, Charlie is something like an arbiter or a judge. Okay, so now the point is whoever plays first in the quantum Stackelberg game, there is an advantage. Similarly, in the 6-qubit protocol, whoever initiates the communication first takes an advantage. What is the advantage the first mover gets? The first mover can read the opponent's message without revealing his message, right? It is not simultaneously exchanging the message, rather reading others' message. Based on that, this party can give correct or incorrect message. So there is a one-to-one correspondence between so-called controller-dependent quantum dialogue protocol and a Stackelberg game. So this generalization is not so simple. It's not possible to generalize to all the game. Very interestingly, this sort of a correspondence has been observed in a particular class. Right. Now, once again, coming back to the question, why quantum game? Why we have quantum communication? What is the link? As I already pointed out, quantum game theory is an extension of classical game theory to the domain of quantum mechanics. So we apply the rules of quantum mechanics in the classical game so that we can have quantum game. Right? Why do we want to do? For many reasons. One of the simplest reason, as per the very first breakthrough paper from Mayer, is quantum algorithm. So any algorithm you thought of can be modeled as a game. And if you solve that game in the classical version, you'll get one advantage. If you solve the same classical game in the quantum domain, you will get much more advantage. So now you make a connection. So quantum algorithm is related to quantum games, right? It's not only that, it also has a very significant role in the quantum cryptography, right? So classical cryptography is extended to quantum cryptography, and the quantum cryptography can be thought of a game, and then the communication as like a communication, and we also think of a cryptography to happen in a secure way, right? In all these notion, right, starting from quantum communication, quantum cryptography, quantum algorithm, we can try to formulate in the form of a game. That is the main aspect, right? Once you formulate in the form of a game, what type of a game? It's basically a quantum game because you're trying to write a quantum algorithm for your problem, right? So when you try to see your quantumness, basically few aspects come into picture. First and foremost, superposition, entanglement, quantum coherence. Without using these things, you cannot leverage the advantage. So you have to have a quantum entanglement and either coherence or quantum entanglement you should have, and you can see the difference altogether. So that is the reason why we venture into quantum game theory, right? So as I pointed out, what is absent in classical game theory, what is present in quantum game theory? Naturally, quantum superposition and entanglement. So the simplest example of a penny flip, wherein quantum strategy used by a quantum player creates a superposition state. When there is a superposition state, he can always win the classical opponent. And the next path-breaking work in terms of quantizing prisoner's dilemma game, wherein quantum entanglement play a crucial role. And when both the players, Alice and Bob, adopt a particular quantum strategy called a Q move, then they can come out of the dilemma. So these two are the path-breaking work, and many such works are coming up in the direction of quantum game theory. It has its own significance in other domains, like chaos, quantum chaos, and all. Right. So now in the recent days, you must come across a concept called quantum finance. So in the finance, in the marketing, stock market, and all those domains, quantum mechanics come into picture. You'll be wondering how it is the case, but it is indeed the case. Because as the stock market deals with a lot of data, right, you have to analyze. You want to make a prediction which stock will increase, which one will fall down, right? For all those things, basically you're doing an optimization problem. So when you're doing quantum optimization, you can accurately predict your answer, and also faster. So these are all the advantages. So quantum finance, in fact, quantum game theory has a very direct relation with quantum finance, quantum biology, and so on and so forth. Right. So there are some open problems. So as I pointed out, for a particular case, quantum game theory and quantum communication, shown to be a one-to-one correspondence. And if we generalize this, then a lot of gates will open up in the application aspect. And of course, people have implemented some of the games in IBM Qiskit also. Very simple games, but not many. A lot of things to be done. In fact, so-called EWL quantization scheme I mentioned, right? ICERT, Wilkinson, Levenstein quantization scheme can also be implemented in IBM, but it is not yet tried. It's not yet attempted. And establishing a quantum financial game using quantum strategy is a yet another domain wherein people venture into, and it will have a very direct impact on the stock market influence and optimization problem. And of course, quantum game theory, as I keep on mentioning, it has a very direct relevance with quantum algorithm, and that's how this entire domain of quantum game theory started off. Right. So these are all the references I have followed, and of course, some of the works what we have published from our research group. So there is a research group in our institute. Uh, so I have a few 6 scholars. They are working on different domain. Some of them, a couple of scholars are working on quantum game theory, and a couple of scholars are working on quantum communication, and the 2 scholars are working on quantum operators. So quantum operators are directly related to quantum circuits, which are very essential aspect of any algorithm you want to design. Right. So with this, I close my session. If you have any question, doubt, clarification, or comments, you are most welcome. I think we have 10 to 15 minutes time for the discussion.
Dear participants, you can post your questions in the chat box also.
Of course, I must thank the organizers. Not many people are aware of classical games as well as quantum games. Of course, a classical game is a matured branch of mathematics. There are very few researchers across the world, and there are journals also available. But when you ask quantum ness, it is not really.
Pigmentation or acne marks.
So people have not tried.
Clinically proven, dermatologist recommended, now available in trial.
Okay, so quantumness of classical game is not yet explored. It's yet another option for people who are working in computer science. Right, there are a lot of interesting problems coming up for computer scientists. Not only algorithm part, but also you can work on quantum game theory, wherein a lot of NP hard problems can be modeled as games. Right. So once you have games, you can look for a solution, optimal solution, and it is technically called Nash equilibrium. And we can also quantize it using well-known framework called EWL scheme, and we can see is there any advantage, quantumness, fetch anything new. Right. These are all the new opening for researchers in computer science. Yes, please. If there are any questions, I'm happy to take it.
Thank you, sir, Dr. Balakrishnan, sir.
Thank you, sir.
You've given a very good explanation about your topics.
Yeah.
Thank you very much, sir.
Yeah, thanks a lot. Thanks a lot. Yeah.
Dear participants, we are going to start the next session. Mr. Murthy Paramasivam, you're going to join within a few minutes.
Sir, good evening, sir, Mr. Murthy Parvasan, sir. Sir, your voice is not good.
Fine. Is it fine now?
Yes, sir, it's audible, sir.
Okay, fine.
Yes, sir.
Thanks a lot.
Uh,
Bye, everyone.
so, yes, sir. Dear participants, we are going to start our session 10. Our today's guest, Mr. Murthy Parvasan. It's my privilege to introduce Mr. Murthy Parvasan, Vice President at Wales Fargo, Bangalore, Karnataka, India. He has a rich industry experience and also he worked extremely in the information security, financial technology, and enterprise solution. He has a lead strategy initiative in cyber security, especially in the designing the secure framework for banking and enterprise application. He delivers his lectures on quantum key distribution and quantum safe cryptography. His deep experience in the finance and cyber security sectors will provide us with a clear understanding of the need for quantum resilient security system in today's digital era. Thank you, sir, for connecting with us. Now session is handed over to for today's guest.
Thank you. Thank you for the nice introduction and also the elaborated view about myself. Thanks a lot. Let me share my screen so that allow to share screen. Allow to share screen. Okay. Hope you are able to see my screen.
Not yet, sir.
Wait just a moment. I need permissions to. Okay, fine. So you're able to see now at least?
No, sir. Yes, sir. Now it's visible, sir.
Okay, fine.
You can make it as a full screen. So
Yeah. I hope you are able to see my screen.
yes, sir. Yes, sir. Exactly.
Okay. Just a moment. Okay, let me start from here. Sorry for the little bit of mess up in the starting. Okay. Thanks for this opportunity to share my experience as well as my interest in this, as well as to share what is happening in this particular field of quantum, and with respect to the security, especially in the security field. So the agenda of this particular presentation or the talk is in the following order. Like first, we'll discuss about what is a classical cryptography. Then we'll talk about quantum cryptography. In this quantum cryptography, we'll see briefly about what are the quantum key distribution trends and technologies, and also about what are all the quantum distribution in the emerging trends, and what are the current research topics or the current challenges that we are we are in. And after that, we'll also see about the post-quantum cryptography, which is about in case if the quantum comes into play, or definitely it is going to come into play. So how we are going to protect our classical systems from classical, what you can say, communications or the classical cryptography, because we are not sure about till when this quantum computer is going to exist. However, it is going to what kind of a threat that it is posing and all the stuff that we will see in the post-quantum. And also we will see about what is the current state of post-quantum cryptography. Okay, so first let us go through about what is classical cryptography means. So if you look at from the current state of our classical cryptographic algorithm, the informations are in bits, which are zeros and ones. And these particular algorithms are built on either finite field or Galois field. That's what we say in terms of either it's a binary field. So the stream ciphers which are defined, or it's bit, byte, or word based. That means to say that single bit at a time to encrypt, or byte in the sense like 8-bit at a time where we can encrypt, or word in the sense it is either it is 16 or 32-bit depending on the computational things, or the registers. So now it is up to 64 bits. So as of now, what are all the encryption algorithms that are defined? Everything is based on in this either Galois field or Galois extension fields. That is including the block ciphers, which are AES or DES or TOFIS or Blowfish. So whatever the algorithms which are done, that is either it is 64-bit of blocks or 128-bit of blocks of data. We are not talking about keys here. We are talking about the data here. And also with respect to the public key that we are talking about, either in the prime field or it is in the Galois field, extension Galois field. So primarily, these are all things can be in this, right? The units can be measured completely, and the values can be copied, and the values can be erased. What I'm trying to say here is like the keys whichever is being used, or the message whichever is being used, or the encrypted data whichever is being used, those are all the things can be measured in the sense like, yes, this is the message that is being encrypted and which is received based on the integrity checks that we can measure it. Measure means to say the information is not altered, information is authentic. When we are decrypting that, we will say that yes, information is authentic because there are no errors are coming and all the stuff. And also it is about the values can be copied in the sense like, be it in a encrypted state or be it in the decrypted state, or mean to say the plain text. The informations can be copied from one place to other place, or one storage to other storage, or it can be storage stored for eternal uses as long as it is not deleted. And the values can also be erased in the sense like it can be deleted completely or deleted logically. The deleted completely in the sense like erase that each and every bit of that entry in the storage level. Logically in the sense like that is what we do in terms of delete command that we give wherever it is there, in either in the disk level or it is in the file levels, wherever we are using the normal delete means delete, but the logical entry is still present, wherein the forensics can bring it out their tools and then get the data back, means data back. So that means to say that the current cryptographic algorithm purely based on digital and on the binary. And if you look at from the current state of the systems which are used for the cryptography, which is based on silicon hardware, mean to say like it is based on either millions of transistors or anything, that is mean to say that silicon hardware. And if you look at from the Moore's law, the number of gates, if you look at from 2020, which is about 2 trillion gates in the 7 nanometer chips, means ICs, or the processors. So, for example, AMD and Apple, they already have more than this. As of now, they are moving towards about 3 nanometer technology, which is having more than twice of this number of gates or the transistors. So these cryptographic things have been built on the dependent technology in the sense like it's not only about the silicon hardware, it is also the subsystem in terms of the memories, the hard disks, the RAMs, and the storages, and the communication channels, like what kind of a channels that it is being used, either it is wireless, wireless, optical, or any such kind of a things. And this is these cryptographic systems are weakened by the advances in the cryptanalysis, because if you look at in the traditional way of looking at the cryptanalysis, the exhaustive things, that means to say the brute force attacks in the sense like either on the system, either on the keys or either on the system as it is, in the sense like the side channel attacks, say for example the power analysis attack, or the side channel attacks also includes tampering with the smart cards which are used to store the keys, and also the thermal analysis, what kind of heat is getting dissipated at where it is, how it is, and all the stuff. So um, and also when you're looking at the key side, it is like an exhaustive search or the conditional search or the means contained search, in the sense like some of the the prime numbers which can be reduced with the primes in P or primes in NP. So that's that kind of algorithms which are being proposed. And then they are also meant to say that on the keys, it can be attacked on the systems, it can be attacked on the side channel, it can be attacked on the protocol level, it can be attacked. So that means to say that the cryptographic these systems are weakened by many ways in terms of cryptanalysis and also cryptanalytic attacks. And when you look at the cryptographic system to replace any algorithms, it is a little bit of a tougher task. Why? Because there are, if at all any algorithm is being, what again, any algorithm is being um, standardized by either NIST or by any other IET of international NIST, in the sense like which is in the US National Institute of Standards and Technology, or if it is by any other X standards, ANSI standards, or any other ISO, or any other this kind of means IET of any standards, if at all, if it is being standardized, it means to say that it is going to be integrated within the products. So suppose, say for example, it was sometime in prior to 2005, 2006, before the AIS was becoming so popular, there are specific engines or specific processors born or defined for DES, the data encryption standard. Same way, when the AIS has been proposed, now if we look at for AIS, there are different, what you can say, hardwares or softwares, or when you look at even the format preserved encryption heavily, which is built on this special mode of operation in AIS, there are special considerations are given with respect to implementation of this in the processor level or in the dedicated little bit of a hardware where the keys are being generated and stored. So if at all we are going to replace any of these algorithms, right, then must be a support system components to execute these algorithms. And we also have to change the protocols which are built around these algorithms. And if at all any new algorithms coming, and then before we are going to standardize it, there must be a validation to take to be done. That means to say that either NIST level validation or any other third party level validation in terms of whether the algorithm is secure or not secure from the structure wise, the primitives which are used within the algorithms, and the randomness and entropy side. So a lot of things will come into play. And also when we are going to implement it, what are the OS components which are tightly coupled with those kind of things? Say, for example, when the encryption is used, either in the file level encryption or the storage level encryption, the operating system components are heavily using those kind of encryption routines. So that means to say that those are all the points also to be changed. And not only this, if at all any encryption or security solutions which are used within the system, if at all you are going to change any cryptography or any other algorithms or any other security related algorithms, if you are going to change, we need to consider not only from this, everything else whichever is using that to protect the information which are either processed or stored or transmitted from those systems. So that means to say that currently anything that we are going to do, anything we are using the this cryptography in a system, which is tightly built with all the components within the system. One way or other, every component is contributing toward the security of that particular system. So if you look at from the encryption algorithm points of view from in the current state, right? So there are stream cipher, which are typically proprietary encryption algorithms, which are in the closed systems. That means to say that it may or may not be published, or it may or may not be standardized. I mean, typically, these kind of things will be used within the very high secure environment, like army or like any other defense forces, or between the high level of communication between the ministries. So those kind of places, these stream cipher will be used. So what kind of primitives or what kind of things are used within this, or the structure of this algorithm, which is little, means it is generally it is not published. But thing is like there are a lot of researches going on in terms of how we can generate the random sequences so that it looks these pseudo-random or nonlinear random sequences, which exactly looks like a actual random, means true random kind of sequences which used to encrypt the data. Either it can be bitwise stream cipher or bytewise stream cipher or wordwise stream ciphers. So very well known kind of stream ciphers are like Snow variants and also Cha-Cha variants. So these are all the stream ciphers which are currently being used within this. However, they are not used to encrypt that data as it is, but they used in a different way in terms of either to generate the keys or any other things. And next one is about the block ciphers, which are generally public kind of an algorithms. Currently, we are using AES and also like some time back, the blowfish or the toefish or some Blake kind of an algorithms were public and they were being standard in IETF also. That means to say that in some of the SSL means secure socket layer or TLS layers, some other times these algorithms also used to encrypt the data either in the TLS or it is in the mobile TLSs. So in a block cipher, the data repeats for every 64 kilobit or 32 gigabits or 18 quintillion byte of data. If you are going to use the data blocks of 32 bytes, means 32 bits. If you are going to use, the data will repeat for every 64 kilobytes. And if it is 64 bits of data blocks, then that encrypted data will repeat every 32 gigabytes. And if it is data block is 128, mean to say that the data will repeat at 18 quintillion of data. So the security of these algorithms, primarily on the key search algorithms, what can means if we are going to use AES in the sense like the keys are varying from 128, 192 or 256 bits, wherein NIST itself, it recommends that do not use 192 or 128 bits of keys if it is a secure, if you're really looking at the secure, highly secure systems. So they recommend to use 256 bit of keys so that the exhaustive search will be very time consuming, and within the given time, it is difficult to get the keys or attack on the keys. So, and also the attacks also based on the linear, differential or boomerang cryptanalysis on either on the ciphertext for a chosen plain text or a ciphertext on a chosen and the modified plain text. It means to say that for these are all the things that you can get the answers in by Googling it. But at a high level, what is the ciphertext on a chosen plain text in the sense, suppose I know my plain text. And when we are giving this to the encryption systems, when the data is coming out, so I'm keep giving the same data at a different interval, different times. That means to say that I should get a different, what I can say, ciphertext, depending on the mode of operations of the encryption which is used in that. If suppose I'm getting the same plain text, then I'll be able to derive the key faster because I know what is my plain text and number of times I'm giving. So I'll be able to find out what is the difference between this, and then I'll be able to get the things out of it, either through linear or differential cryptanalysis method. And ciphertext for a chosen and known modified plain text in the sense like I know my plain text, and then I'll modify one or two in the plain text in a data that I'm going to give it to the cipher system, and I'll collect back, means I'll collect the cipher, means the enciphered or the encrypted data, and I will look at what are the changes are coming whenever I'm giving a 1 bit of or 1 byte of data or 1 bit of data or 1 character that I'm changing, that what is the output that is coming, so that either through differential analysis or the linear analysis on this, we'll be able to calculate what kind of encryption keys that is being used. Once we get the keys, then it is very easy for us to break the systems, because the key is the main thing that is always looked at as the security parameter on this. So this is with respect to the private key encryption or the encryption algorithms. When you're looking at from the public key encryption algorithm, which is based on which is built based on the computationally hard problems. Either it might be on the prime number generation, or it might be based on the discrete log problems. So there is no proof of the difficulty of any of the underlying mathematical problems. That meant to say that there are a lot of proofs are there that some of it can be broken, but thing is like it is working on the time it takes to break these systems. So one of the things is like known prime factor problems, which is based in exponential time factor algorithms, and also some of the algorithms are based on exponential of the log by 2 computations required to find the factor when the composite number is in a prime field. And also there are some of the algorithms are there in the polynomial time factoring algorithms, and which requires a log n of computational effort. So these are all before quantum is coming into play. These are all, it is looking on a traditional way in the sense like, because it is a sequential kind of an algorithm where there is no parallelism exist. So the recent trends on the either by the Shor or by the BB, I mean Shor, Peter Shor, who demonstrated that there are quantum algorithms which can easily compute these keys in a quantum computer. So this is possible if we have a quantum computer and which can perform the quantum computing, then this can be broken. So as of now, when we look at from the quantum computer side, so we have quantum qubits. That's what we used to say. We will just go through it. So we have practical quantum systems are there with 50 qubits, 100 qubits, and people also used to say that there are thousands of qubits of computers and other things. So I'll just a little bit brief about this in the coming slides. So this is all about the current state of and the current domain of cryptography, and as well as the algorithms and the systems that we are in, and we are using those things as of now. And the security is based on the root of the ETH root of n. That means to say when if it is RSA problem. And the finding a factor using it's an exponential and polynomial algorithms which are very computationally intensive, in the sense like if you are going to break the 1024 bits of keys, it takes about they mentioned about somewhere about 10 power 100 or 10 power 200 kind of an years that it takes about. So that's what it was mentioned theoretically if you are doing the exhaustive search. But there are a lot of things have been come, and then it means that even if you are not able to break the exact keys, even if you're having an equivalent kind of a case, and then if you can extract our 20 to 30% information, we'll be able to get the remaining, that is the information that what is there in the encrypted data. So that is those kind of things are after computing all these things. So currently it was recommended to use minimum of 2048-bit keys from the RSA side. So if you look at from the quantum side, using the quantum properties, instead of going with the exponential and polynomial algorithm, means exponential and polynomial time algorithm, then we can solve that only in the polynomial time. That is order of n instead of order of n square or order of e power n, something like that. So if you look at from the discrete log, it is finding the root of r mod p minus 1 for a given curve. Okay, so let us go through what are all the how the quantum is evolved, and what is the quantum cryptography that is currently being, what I can say, developed or being used within among ourselves. So in classical one, we mentioned like it is based on the bits of zeros or ones. Here we call that information is in quantum bits are called qubits. So there we say it is at the state either 0 or 1, but here it is written as the combination of either it will be in the state 0 or state 1, or any other state linear combination of these two states. That means to say that it can exist as 0 or it can exist in 1, or it can exist anywhere in between 0 or 1. Between 0 or 1, there are infinite many possible combinations are there in that. So that means to say that comparing with the binary, this is this system is working on the um, photon levels, not on the electron levels. Wherein if you look at from the semiconductor wise, there is a cutoff region, there is a saturation region, there is a cutoff region, and there is a linear region. So in the linear region, the current is almost it increases constant. But when it is coming to the photon, it works on the photon, which is either based on a wave particle or or on the light particle. So it is having both the properties of this. And the units can be measured partially with a given probability. That means to say that if we are going to measure a state, it can be 0 or it can be 1 or it can be either any of this. That means to say that there is a probability also involved in this. With this particular probability and this particle is at this particular position at this particular amplitude or whatever it is that we are going to measure it. And once we measure it, the details are altered because of the photon principles that are applicable when we are doing the measurements. And another thing is like these quantum computer, the values or the say states cannot be copied and it cannot be erased. That means that it exists, but you cannot copy and then store it somewhere that this is the quantum system or this is the quantum parameters or this is the quantum values or bits or whatever it is. It cannot be stored in a quantum state. However, if we measure it, we convert it into binary, we should be able to move it to, we should be able to copy those binaries which are equivalent to that particular state when we measure it. But the moment we measure it and then we leave the systems open again, then again the system will go into the quantum state. That means to say that we will not be able to measure the same quantum state again once the measurement is over and then we release the system from the measurement. So that means to say that we cannot copy, it cannot be erased, not like the digital ones. And the properties of qubits are is like the states are in a single qubit, which are zeros and one, I mean the 0 state or 1 state. And the quantum state of a qubit is in a superposition of 2 states with a complex amplitude for each alpha and beta. That is generally it is written like this. Alpha, it means the state will be written like this, psi is equal to alpha, alpha times 0 state plus beta times 1 state. That means to say that alpha and beta are the probability of that particular state 0 and the probability of state 1. Wherein the probability is the whole probability of occurrence of 0 or 1 is either 0 or 1 is 1. That means to say that alpha square plus beta square equal to 1. That is the probability. And the quantum state of 2 qubits is superposition is 2 qubits. When you're having the superposition is 4 states. So that means to say that if you're having n qubits and your superposition is 2 power n states. So to double the power or in a digital computer, you have to double the bits. That means to say that if I'm going to use a 16-bit computer, if I want to multiply, if I want to get the 32-bit output in the sense like I have to use two 16-bit to get the output. That means I have to double the bits. But wherein if I have to use the double the power of qubit, I have to simply add another qubit. So we are talking about means if you look at from 1 qubit, we are having 2 states. 2 qubits, you're having 4 states. So that means to say that if you want to add if you want to double the computational power, add 1 more qubit. So that is the properties of qubit. And another very important properties of qubits are like no cloning, that we have seen that we cannot copy it. Interference of light, I mean to say that it improves the probability of obtaining the desired result by the constructive interferences, and also diminishes the probability by obtaining the erroneous results by destructive interferences. So these two things which should be looked at very carefully in terms of the interferences, whether it is a constructive or it is a destructive. So you can look at, for example, you can study about the experiment carried out by Feynman using a moving slide particles of the windows. So you'll be able to understand what is this, how this interference actually works, and then what kind of whether it is a constructive, destructive, how we can make it out. So that will be a really good example in terms of you can go through that and you can get to know really how this interference actually affect the qubits. And also the measurements, as I mentioned, it disturbs the quantum state, and the state is transformed from the complex superposition to a simple state when you are doing the measurements. That means to say, from the qubits, we'll be able to extract the digital level bit level, that is zeros and ones. That is where that currently we are doing the computation. If you can do the computation and then do everything in the quantum world and using the quantum algorithm, using the quantum processor and the quantum means quantum computation, then we no need to have this kind of a state transformation. However, when you are doing the any measurements to work with the current systems, this will be transformed from the complex superposition state to the simple state, wherein so that we can work on the bit level using our classical computations. So the superposition in the sense like it is what is the superposition of a qubit? It is every quantum state can be represented as a sum of two or more distinct states. A qubit is in a superposition in both the states. Mean to say it can be there in the state 0 or it can be there at the state 1 at the same time. That means to say that if the state is measured only one or the other state with some probability, even if it is repeated. That means to say that even if you say that if the measured output is 0, and that means to say that any number of time with the same state, same kind of equations at the same place, it is going to give the same output, that is as a 0. If it is given as a 1 at any point of the time, only if you are doing on the same kind of a state, any number of measurements if you are doing, it is going to give this measurement as output as 1. And entanglement is like about the John property of the 2 or more qubits. And the entangled pair is a single quantum system in a superposition which are of all equally possible state. That means that if you're that is what we have mentioned in the previous also, 0 and 1, it is a 1 qubit. And if it is a 2 or more qubit when it is there, all the states can be exist with the equally possible states. So if one of the state is changed, then all other states will be adjusted instantly to be in the considered of the quantum rules. So if a measurement is made on one state, then others will automatically collapse, and then the output it will be the same. Means output it will be whatever you are getting is based on that particular state and its equation. If you are going to leave that systems and then you are going to measure it another time, then the output it will be different because the measurement is the state is being the qubits are in a different state. So how this quantum computing, because we just saw about quantum and then I'm jumping from quantum properties to quantum computing. I'm not looking into how it is built and all those things. I'm going directly into quantum computing. So sure, that because that is what we are going to talk about in terms of a security. So what in 1996, Peter Shor, he showed that it is possible to solve the integer factoring using a quantum algorithms. We should be very careful on this. This is a quantum algorithm, not the classical algorithms. So what he showed is like integer factorization is possible by using a quantum states in a quantum computation of bits when they are applicable, when they are computed in the quantum states, and when we can find out the period of it. So basically, he applied a Fourier transform of the integer factoring and also the discrete log factoring algorithms through a Fourier transform. So he proved that the solutions of eth root exist, or nth root in RSA that also exist if you can compute the period over which there is discrete log problems or the prime number problems are currently being worked on the crypto systems. So this is his algorithm is based on a hypothetical quantum computer. I mean to say that he assumed that there is a quantum computer exists. What he proposed is a quantum algorithms. It's not the computational method. he proposed a quantum algorithms where you can compute the nth root or eth root of the problems. So the implication of this Shor algorithm is like current ciphertext is available to the attacker, and there is a quantum computer which is available, and also the attacker is applying the um, uh, harvest now and decrypt later. That means this is the output of the Shor's algorithms that mean to say, yes, these keys can be broken. These keys can be retrieved when we have the encryption. When we have the quantum computer. So what currently that is being whether it is happening or not, that we are not really sure about it. And so among the industry, the things have been, or the thought process is like attackers are right now collecting the encrypted data as much as possible. Either it is of the finance industry or of the any communication between the nationals or whatever it is, any sensitive data or any communication which is happening, they are harvesting the data. Mean to say that they are storing the data, assuming that there is going to be a quantum computer which is going to exist or which is going to be built, and then these algorithms can be applied. That means to say that they will be able to get the key and then they can decrypt later. So that is the kind of assumption it is going on, saying that yes, there are lot of data is being harvested. Mean to say that it is stored at the attacker or whoever it is, the interested party who wants that encrypted data to be decrypted at a later point, because some of the data are very sensitive, which need not to be disclosed to the world at any point of the time. Some things might be disclosed at very particular times based on the lifespan and other things. So that is the things are being happening among the users or the attackers. So that is assumptions that this Shor algorithm created. And if you look at this Shor algorithm, it is purely a probabilistic algorithms, which is defining the eth root of n in the RSA problem, where it is calculating the period or using the quantum parallel algorithm and based on the quantum Fourier transforms and other things, and also using the it not only uses the quantum computing part, it is also using the classical computing part as well. I mean to say that how the remainder is being calculated using the normal Chinese remainder theorem or GCD, that is greatest common divisor. So which is finding the factor n based on the period is based on either the remainder or the period or the remainder of it. So that means to say that this is a typical, the left side, whatever is that, this is a typical discrete Fourier transform wherein the period it is repeating after a particular number of bits. That we can see very evident on this. And if you look at from the quantum side, this particular algorithms, if you look at this, the this is calculated using means in a Peter's paper. This is talking about finding the root of nth root, means root for in a prime which is of 255. So if you look at here, there is a period which is coming out of at every instance on this. So you can say that close to that the prime factor exists. That means to say that there is when you talk about the eth root, the eth root exists closer to any of these places. So when we apply these values into the GCD or any other algorithm, means the factor algorithms, then we will be able to say that yes, if it is congruent to 1, then we can say that is the value. If it is not, then take the other value and then put it. So that means to say that is why it is telling it is about in the polynomial time. So let's see, and then in this current section, we will see about what are the quantum key distribution, in the sense like how this key distribution can happen using a quantum hardware. So first we saw about the classical computers, classical systems, classical cryptography. Then we looked at what is a quantum computer, what are the quantum parameters in the qubits, what's the parameters, what is the algorithm it is there, and other things. Now we will see using this quantum computer, so not quantum computer, is the quantum systems, how we can distribute the keys. So here we are moving to the quantum hardware side in the transmitter and the receiver, not in the processing. So that means to say that there is no quantum computer used here as in the quantum key distribution technologies. However, the hardware and the protocol used are based on quantum. Mean to say quantum, how the keys can be distributed using the quantum hardware and also the quantum channel that we'll look at it. So in a traditional key distribution, if you look at, so there is a plain text from the Alice going to be sent in a classical channel, and Alice will and Bob, they will share the key using a classical asymmetric cryptographic algorithm used in a classic channels. So once the key is exchanged, then the data, whatever the plain text is there, using the symmetric encryption or decryption algorithms, whether it is encrypted and sent to Bob, or Bob will share the encrypted data to Alice. So in our case, in our discussions, we will say that Alice is encrypting, Bob is decrypting. So, but it can happen vice versa also. But for our discussion, our presentation, we will restrict our discussion with Alice is sending the encrypted data and Bob is decrypting the data. So in the traditional data key distribution, it happens over a classic channel, and the asymmetric algorithm, which is used to take the send the exchange the keys between them in a encrypted or secured format. However, let us, if you look at the need for the quantum distribution, in the sense like this, we already seen why we are, what is the key exchange algorithms, why we need a quantum algorithm that we have seen already. So in a quantum key distribution, if you look at the quantum key distribution is an hardware component here. There is no software that is being used in this. However, the protocols may be using the software and other things, but the QKD is hardware. So the quantum key distribution exploits the law of the two entities, which happens in the real time. That means to say that if in a previous case, if you look at Alice and Bob and they want to transfer, they will transfer it and they will they initiate it. Suppose Alice is initiating that I want to transfer something to you. Bob has to accept that they want to. Yes, yeah, we can initiate and all the stuff. That means to say that there are logical things and logical states are being involved in this. However, when it is coming to the quantum key distribution, it is a real time. It happens. That means to say that when Alice is telling that or Bob is telling that they want to communicate to each other, that means to say that they have to start the QKD in a real time. That means to say that it will not happen in the we cannot do in the logical kind of things. That saying that yes, I will store the keys and all other things. That is not applicable here, because the quantum principle wise, we cannot store the keys. We cannot modify any of the parameters, including the amplitude of the keys. Okay. So that means to say that whenever when Alice want to transfer the keys, the keys are not generated using any other algorithms. It's all plain zeros and ones only, or the actual keys that however they generated off the channels. They will take this the keys. Alice will take the keys generated out of the key generation algorithms, and the data, the keys are not encrypted. The keys are sent to Bob using the classic combination of classic and quantum channels, and it is received by Bob. So here there are different what you can say classical and quantum channels been depicted here. Let me explain about each of these how they are used here. So in a key exchange, right, the classical channel in the key exchange, it is used to validate whatever the information which is being sent over the quantum channel is correct or not all the bits, not all the data, some of the data. So, and also there is an assumption saying that the classic channel is monitored by Eve occasionally, not always. That will come to that later. So, okay. So when Alice want to send it, they will send, she will send the data, the plain means zeros and ones, unencrypted data, plain text data only, plain text keys only. She will send it over a quantum channel using the agreed quantum protocol. Either it is, we'll see those things, what are the protocols. So using the whatever may be the protocols, she will send the details to the Bob. And Bob, upon receiving, what he will do is like he will do the measurements of the data that whatever he received. And he will say that I received this data with this particular based on the protocol type. You will say polarization, or you will say what kind of a classical state or in the mixed state, what kind of things that they are using in the quantum mixed state or quantum classical state. He will say that yes, this is what I received or in a classical channel, and Alice will validate, and then she will say that okay, fine. She will say yes, it is good. Then Bob will retrieve all other details based on the whatever the data that is she is sending, and he will measure, and then he will calculate the keys in that way. So once this is done, then Alice will send the encrypted data using the keys whatever she sent to Bob in the mixed what you can say quantum or data, which means the key which she already sent. So here in the classical channel, the data is going in encrypted mode. Right. So this is the same as one as of current one. However, only the key is distributed in the quantum channels here. Since because the measurements or any of the quantum properties which cannot alter the bit states. So the key distribution, that is what I can say assumed to be secure. So these are all as of now it is on the assumptions and also based on the quantum properties and also the quantum what I can say properties and the quantum measurements algorithms that is being currently used. So that is why it is telling that it is secure. That is how it is being currently, they are being assumed and then being used. Suppose he is coming and then he is monitoring the classic channel as well as the quantum channel. So quantum channel is monitoring continuously, but he is monitoring quantum channel not discretely only. It's not a very continuous, or he is not doing that. He is not taking care about much on the what is coming on this classical channel because it is difficult for him to interpret. However, in the Eve, when he is monitoring, that means to say that he can see what bit is going in. Means he cannot see what bit is going, means he know that something is going in, and if at all he wants to either measure, that means to say that that particular bit is disturbed, because quantum state wise, once there is a measurement, the state is disturbed. That means to say that Bob will not receive the same data whatever is in by Alice, because the states are disturbed. Even if the Eve is, or even if he is calculating and then he is sending the same bits, he will not be able to send the same value as again, because that is not the quantum property it is, because at least it is by if it is there is if it is modified, if he is calculating, at least the value is little bit of normalized. That is 1 by if it is alpha plus beta that we have seen that one. So at least by the modular value of that, it is little bit disturbed. Okay. Is anybody is having a question on this? I could see some background noise.
Hi, I have one question regarding this classical channel. Do you think
Yeah.
this is the symmetric key encryption that's happening?
Yeah, see, generally data encryption happens using a symmetric key. Public key encryption, they will not be using because it's a computationally intensive. So generally, they are not used for data encryption. They used to they generally in the classical side, only for the key exchange we use the public encryption algorithms.
Because in a real-time situations, this when the Alice and Bob communicates over the classical channel, it communicates only the bit informations, not overall that, because they don't need to encrypt all the time using the same key because the channel is really authenticated.
No, in what context that your question is?
I'm just question is in a real-time situation.
Yeah, real-time situation when we look at it, right? So the channel, the data encryption, I'm talking about a data encryption. Data encryption happens using the symmetric encryption algorithms. And the key used for this symmetric encryption is exchanged using the public encryption algorithms. So every time you are initiating a new, what you can say, handshake, the keys are different. Not the same keys are used.
Because in a reality, in this case, in a reality, in a real-time situations, you will not end up with a good number of secret key rate. Because in a real-time situation that you will lose entire key systems, because at the end of the day, what the Alice and Bob do at the privacy amplifications is that they will remove what are the bits they have communicated during their classical communications and whatever the communication they have done it. At the end of the day, if this is the case, that they will end up with a 0-day secret key rate.
So you mean to say you are talking about the key exchange between them is a quantum channel?
In the classical channel. Quantum channel, they only communicate via the photons. So they only encode the informations on the photons. They will send it, whether it is the BB84 protocol or either it is the ACARD or whatever the protocol they communicate. Once they have created the raw key from this quantum channel, and then they will implement the classical channel to ensure that they have measured the Alice and Bob measure in the same polarization state, or either the different one, or either, and then they will communicate the syndrome of the keys which they have generated during the quantum channel. During the quantum communications. Once if they have done this one, and mainly they will first they will authenticate the classical channel. They ensure that the key it's coming from the Alice and it comes from the Bob. And once they have done it, and they will only talk about the syndrome of the key. They never share any keys or decrypt or encrypt any keys or decryption with any keys, because it's already authenticated. So once in this case of in a reality, if the experiment is happening in the reality, if this happens, if every time they will handshake and give a token for the handshaking, and at the end of the day they will end up with the 0 secret key rate, because at the quantum key distribution is mainly about how much secret key you will get it or generated from the key distribution experiments.
Yeah, so when we are talking about in the classical channel, right? Okay, so here we generate the keys using the you generate the keys using the system entropy and other things, right?
Yeah.
So entropy is considered here. So from the entropy source, you are generating the bits or random values as a key. And then you packetize that as a AES key or any encryption keys.
No, actually, I am agreeing in the classical channel encryption. I agree with this classical channel encryption. I'm talking about this quantum channel encryption. So once if you have this, sorry, you please continue the talk, and I don't want to disturb you with questions, and we will talk at the end. Sorry.
Yeah, that is fine. Absolutely. See, when you're talking about the keys for every communication, whatever they are going to use the encryption keys, whatever they're talking here, mean to say that they are, if at all, see, once the transmission is over, they may close the channel. If at all they are going to encrypt again, that means to say that new keys, new ways, new generations, and new encrypt means same encryption algorithm, but the keys are different. So that's how it goes in the practical also. That means to say that they have to establish every time whenever they are communicating. That's how the keys work, because then now if you are repeatedly using the keys, then there is no security in that.
Suppose in case, because the channel is authenticated in the classical, because in the quantum key distribution, the classical channel is authenticated. So suppose if I give you the 100 bits which is generated during this quantum quantum key distribution, that when they are communicated through the quantum channel, you end up with the, let's say, 100 number of keys. But when you have the 100 bits of the string, that you will lose 50% of the bit. That is
practical. That is a practical
Yes.
challenge. What I'm talking about is how it works, the challenges and how we are measuring and other things and all is assumptions. I'm not going deep into this. I'm just covering here how it is working.
I got it. The only thing is I don't want it to just like the symmetry key. It's just a little bit disturbing me. That's it.
I'm talking about data encryption. I'm not talking about anywhere else. I'm talking about how the data is encrypted. That's it. Because we don't have quantum encryption right now.
We do. Okay. Please go on. I'm sorry.
Yeah. So what we are talking about here is about the currently existing strings, which is used in a current QKD. We don't have the quantum encryption algorithm present between the source and the destination. Though we may have the algorithms present, or in a practical also it is there, but it is not commercially being used. It might be used in the research purpose or in the research labs, but not in commercial, that these are all currently being used. That's to my knowledge, because there is no standard. So what we are talking about is like the E, even if he is tapping these things, he will not be able to measure it. Even if he is measuring, that means to say that the channel is, Alice and Bob will come to know that there is an intruder, so they'll abort the communication and then they can start the communication later point of the time because of the quantum properties. So in quantum distribution and encryption is like the transmitter and the receiver are in a QKD, and they are using a QKD link, means quantum key distribution link to connect them. The QKD transmitter or the QKD transceiver encapsulate the set of hardware and the software components within the defined secure boundary. That means to say that within the Alice or within Bob, but the channel which is not under what I can say secure boundary. The link relies both on the quantum channel and the classical channel. The classical channel is used to exchange the classical information for the synchronization and the key distillation between the Alice and Bob. So that is what it is given here. One means it is the transmitter and there's a transceiver. One and two, that is 1 and 2 is the transfer capabilities, and the 3 is the channel, and 4 is the quantum channel, and 5 is the classical channel, which is used for the information things. And the eavesdropper, when they are monitoring, the quantum channel is continually monitored and corresponding to the classic channel discretely. You cannot measure the quantum information as it alters the state as per the quantum principle. So this is the what I can say. I would like to say about the introduction towards the QKD, and this is a hardware when we are considering about the implementation part, and the software part is the protocol. There is no, what I can say, like software is being developed and then built around and all the things when you are talking about the quantum key distribution. So there is a protocol. Yes, that's the software side. And the hardware side is how it is the transceiver, their work. And also you cannot copy the quantum states as per the quantum principles. And even if the measures, Bob will, Alice will understand that the channel is not safe and they will abort the communication. So if you look at from the methods of QKD, there are different methods are there. Either it is a continuous variable or discrete variable or the measurement device independent QKD. So if you look at from the discrete variable, in the sense like the protocols work on the Hilbert space, where the quantum state used for coding is a finite dimensional throughout the key distribution process. and it's based on the light source and the properties like phase, polarization, or time bins of the photons. And the coding with a number of polarization and detection, and also the relative phase of the photons. And it is this particular discrete variable QKD is mature about all other QKDs, because currently we are using the optical channel for the means for our classical communications. So it is easy to exploit that. However, there is a challenge here is like, since it's a QKD generally works on the point to point when it is coming to the channels, we will not be this will not this will not go through the classical way of the how the optical signals send, in the sense like it sends through the repeaters, amplifiers, and all other kind of systems. But in a quantum, when the transmitter sends the data, it cannot be altered or it cannot be used by any other amplification method or the repeaters to alter any of these values, including the either the amplitude or any other intensity or any other things that is being on the photons, because anything else comes into that, it alters the state of the photon. So that means to say that this generally it works on the point-to-point kind of communication. However, there are a lot of researches being happening on this, how to increase the length of it. So how that what is the current length and then current kind of thing that we'll see in the coming slides. So the QKD, I mean the discrete variable QKD is based on the prepare and measure class of protocols, and it is and also the entanglements based protocol and the distributed phase runs protocol. So these are all the different types of quantum key distribution protocols that are being used with a discrete variable using the light source properties. However, when it is looking at the continuous variable QKD, it is like it is a class of QKD protocol that Hilbert space is used to coding is infinite dimensional, and also the continuous through the key distribution process. Something like we can if you are comparing that, I'm not exactly telling about this is how it is, but comparing with analog communication versus the digital communications. But do not just map it on this. Somewhat equivalent to that, I'm just trying to say on this. And the continuous variable based on the quadrature components of the quantized electromagnetic fields, and the coding with the number of number of polarization the direct relative phase of the photons. It is not relatively mature. Sorry, there is a mistake here. It's little bit coming up in this, and there are a lot of research is being currently focusing on this, because this is giving a this is used in the larger distance, means for it is in for the larger distance of communications. So some of the protocols are like a squid state protocol, coherent state protocol, and entangled state protocol. That is the different types of continuous variable protocols. When it is coming to the measurement in device independent QKD, in the sense like, so there is a between Alice and Bob, there is one more trusted person is there. He will receive the data and he will measure it. He will look at it and then he will send it to Bob. That means to say that person in between is a trusted party. Okay, so that we can say as like a Charlie in the middle. Alice and Bob will have a transmitter and generate and quantum state signals to Charlie. Charlie will perform the Bell state measurement to project the incoming quantum signal into Bell state, and then publicly announces the measurement to Alice and Bob. Then they will assuming that okay, whatever their information they are receiving from the Alice and Bob, that is the bit, and then they will be used to that for the further communications. And currently, another things also being research is going on in this, like a device independent QKD. That means to say that without any third party. So that is also research is going on this. So let us see about what one of the protocol, that is BB84 protocol, which is Bennett and Brashard, and which is proposed in India in 1984. At, if I'm correct, it is at IIC, in one of the international communication conference. And so in this, the BB84 protocol, which is work on these are all the different states of that. That means to say that first state is about the qubit preparation, and second is about the shifting operation, where Alice and Bob respectively share the encoding measurement basis, means in the classical channel, and it can be the classic channel, maybe a fiber also. And there is they will also do the parameter estimation in which they calculate the quantum bit error rate, and by shifting the keys to verify that the whatever the data means the bits transmitted between them is in the predetermined threshold value. And when it is coming to the post-processing, Alice and Bob will perform the error correction verification and then communicate to them that this is what are the details or the bits they got it through the classical channel to arrive at the final key bits. And authentication is about the first key session is authenticated means and using the full pre-shared with the pre-shared key between Alice and Bob. And after that, they will be doing the data exchange, encrypted data exchange after that. So this is the BB84 protocol, Benes and Brashard, that is the protocol that is used. And there's a little bit of a detail that is given in this. This is on the discrete variable QKD. In the continuous variable QKD, which is based on GG02, that is, these are all the authors' name. They proposed this protocol based on the continuous variable things. And this also having the similar kind of a thing, however, the process is a little bit different. So Alice prepares the coherent state and using the X plus JP, where the X and P are the real and imaginary component of the electromagnetic field corresponding to their quantum state. And this state is sent to the current, that state is from Alice. She will send the state to Bob. And Bob randomly measure the state and on the quadrature of the coherent state and record the measurement is made. And then he do this similar kind of a shifting operation based on the quadrature measured, and then he'll send it to the similar kind of a details to through classical channel and the parameter estimation, and after the post processing and also the authentication, and then the communication takes place between the between them. So this is the protocol, means continuous variable protocol. So some of the typical QKD protocol, which are like BB84 means, and the year and also the approach. So the BB84, E91, BBM92, GG02, these are all the author's name and also the year that is they published, that is Hawaii, that is, these are all the details. And most of them are, it is on the discrete variables, and some of them are continuous variable QKDs. And also we can see that what kind of approach that is being used on each of the protocols. One is a majority of them are based on the prepare and measure, and few of them are entanglement based. So, and another one is about the research wise, when we look at the transmission media. So since the both the transmission media, be it optical fiber or be it a free space, both the current communications are currently being used. But when it is coming for the the optical fiber, it has a low loss and has a high stability, and it is more suitable for transmitting the quantum signals. And experimental results is like the more the bit rate and distance will be lesser. The lesser the bit rates, distance will be more. So that means to say that at 1.2 Mbps, currently this has been tested on a 50 kilometers using the fiber link. And at the 6.5 bits per second over a 405 kilometers fiber. So these are all the current results that is on the research that has been tested and also proven that this things means to say these QKD methods have been done. So, and also that in a recent demonstration that the fiber-based QKD scheme can reach between the 600 to 500 to 600 kilometers. And in the free space, the link is having advantage of wide coverage and the high flexibility. They can be readily, it is available based on our other communication systems. And experimental research shows that air to ground QKD is about 20 kilometers between the point to point, when to say that from the ground station to the flight. And between the Earth orbit to the satellite to the ground station is about 1,200 kilometers. And the free space QKD over the 53 kilometers of the daylight. These are all the current research that has been carried out. So the propagation loss scales exponentially in fibers. I mean to say that we will not be able to, because of the quantum properties and the fiber transmission properties, without what I can say amplification, it is difficult because of the loss. While it is only quadratical when it is coming to the free space, and it has become even negligible in the vacuum that is above the Earth atmosphere. So that is why the but reaching above the between the satellites, it is easier, but from a satellite to Earth and Earth to other places, it is a little bit of difficult when you are using the QKD methods. Okay, so when it is coming to the future research on the QKD method, this paper, it will give the details about what are the evolution of current QKD distributions. So some of the details, whatever I discussed, or I taken from this particular paper, and some of the discussions are from the other different research papers, either by Bernard Brashard or we can say like what are the authors like from the Cambridge, and also some of the authors from most of the things are from the survey papers on this. So these are all the sorry. These are all the research on the QKD methods that is currently being done. These are all the problems that can be also taken from the future research as well. That is either from the QKD networks that side, or the integration with other technologies with like PQC or blockchain or Internet of Things or the wireless networks, and also like in the network and the QKD network itself, like what kind of codings and error corrections, and also the performance enhancement and the commercialization in the sense like how noise free or how error free kind of things that we can bring in. And beyond the QKD, if you are looking at what kind of a secure direct communication is possible, what is the quantum internet, which is already being worked out, kind of what kind of a quantum internet things are there. I'm not covering that here in this because that is a little bit of a pure in the technical side, which I do not want to bring it that here in this. That is away from the topic of discussions. So I'm not covering that here. So these are all the open problems, as well as from the commercial research, research problems from the education institutions, as well as the um, uh, uh, industry vertical side. That, for example, if it is coming to the IoT, Internet of Things, and quantum related QKDs, how it is coming. So what kind of QKD technologies that can be used within the sensors, within an automobile, or between the automobile, or between the automobile to the either the service center or the owners, or to the other authorities, so transport authorities, and in terms of fast tagging, this, that, everything, it is coming. So what kind of applications can be possible on this when it is coming to the IoT and the blockchain, in the sense like what kind of things are applicable from the finance sector, or in the legal sectors, and also the wireless networks, and whether it is again how they're coming into this. So there are a lot of open things are there. If you want any other details, you can refer to this paper. That is the evolution of quantum gate distribution on networks, which is published on 2022. So now let us go to the post-quantum cryptography, which is a pure software-based approach, which is nothing but as I mentioned before, the assumption is that attacker is having a quantum computer, and which breaks the RSA and ECC and other finite field discrete algorithms in polynomial time. So in this, symmetry key is also affected, but it is not given much of the importance in terms of how that encryption algorithms and encryption data, how it is being altered, how it is being what I can say decrypted, and also that is not being much of the things here in this, because the moment we get to know about the key, it is easy to since we have the ciphertext, we have the key, and then it is easy for us to work on the decryption side. So we don't have to really break in terms of how the quantum is going to help in analysis of data. That is anyway, that is a different research problem that is being already been worked out on this. However, it is not much focused on the block ciphers or any other encryption, data encryption side using the stream cipher or the block ciphers, because once the key is known, then it is immaterial of whether we know how it can be applied and all the stuff. And so the post quantum is like, uh, and also like what are the other encryption algorithms that can be resist even if the post quantum is coming into play, right? So the algorithms which are considered are lattice based algorithm, which is based on the model learning with errors and model learning with the rounding model, LWS or LWS. So the post quantum and the industry standardization wise, if you look at the NIST proposed PQC standardization, which is what are the algorithms, even if the quantum computer exists, which can resist or which will not be able to apply the quantum algorithms on this set of either key exchange algorithms, so that we'll not be able to break these algorithms and get the keys out. So that is from the NIST standard, which is from the US side. And also there is another one is like Quantum Safe Cryptography Consortium, which is industry wide, which is a common, which is consortium which has been started by Microsoft, Intel, IBM, and Google, and having the dedicated research on promoting this cryptographic means quantum safe cryptographic method. The goal is to provide industries with the guidance of how to transition the classical cryptography solutions in a phased manner to move into either quantum resist or quantum based. But as of now, it is like the industry is working on moving to quantum based. As we discussed in the first itself, it is very difficult to move from existing infrastructure to a quantum resist things, because since it is tied up with the as I mentioned, everything else in the computing system or in the either within the computer or within any applications, there's security is tightly coupled with the current encryption or any other cryptographic algorithm. So to change in a phase, it cannot be changed overnight. It need to be changed over, means in a phased manner only. We mean to say that, okay, what kind of a checksums are being used? Okay, replace that with the quantum resisting. What kind of a key exchange is used? Okay, change it. And what kind of entropy systems are being used? Change it to this one. Change it to quantum resistant entropy source. So that is how that phased manner we can do it. We cannot do it overnight, saying that okay, everything we can remove it and then we can put into all the quantum protocols and everything, and then we can do it, because there is a system compatibility and all other things need to be worked out. And also like another one is from the IBM and D-Wave, which are providing the quantum computing as a service, in which allows enterprises to test their cryptographic solutions against the quantum computers. This also will provide the strategy in developing the quantum resistant cryptography or quantum resistant algorithms. In the post-quantum cryptography, which is referred to that are secure against even the quantum computers are present. That means to say that it is by the developing a protocol, cryptography protocols we use in the PQC, which will resist the quantum algorithms, so that the mathematics behind are intractable even in the presence of a quantum computers. And the post-quantum cryptography is a solution which is based on the same principle of the cryptographic method that is currently being used. That means to say that the PQC is still based on binary. It is not going to use any of the quantum, what I can say, algorithms or quantum things and all the stuff. No, it is not going to use any quantum properties or quantum algorithms in this. It is still the binary, but the only thing is like the algorithms and also the basics behind it. I mean to say that from the number theory and the Galois field is going to be the same. It means finite fields only. But thing is like how it is being used currently, it is based on the polynomial and also from the number theory and other things. But currently, these things are being currently considered or based on the lattice because it is having a different dimensions, and the dimensions can increase based on what kind of measurements that you are means the learning with errors as well as NTRUs and other properties of lattices that you are considering here. And also the protocols are still vulnerable. These PQCs are still vulnerable. That currently no quantum algorithms exist to attack these PQC algorithms. That is the assumptions. So as with the current state of this one, so at least it has been projected for next 10 to 15 years, saying that, okay, the quantum computer, the quantum algorithms with the current state, with the current kind of evolution, it is not possible to have such a kind of an algorithm which can attack these PQC algorithms. So the current state of PQC is like there are different algorithms that are being proposed by different people, and then it is the kind of evaluation is there going on for from 2020 till last year, and 2024 December they announced that different algorithms for different uses. That is lattice based. So the standard is like NIST approved that FIPS 203, 204, 205. In 203, it is like there is a lattice based algorithm which is based on crystal Kyber used for key management, key encryption and management. And which is advantage of this is like it is having a strong security. These are all with respect to the current existing known algorithms, existing known quantum algorithms that are there to which are there to attack on or the analyze cryptanalyze the these encryption algorithms. Means sorry, these cryptographic algorithms. So advantages is that with considering the current current quantum algorithms, it is strong. Mean to say that it is fast and efficient. It's relatively small key and the ciphertext sizes and good performance on the embedded systems. And disadvantages, it is the keys are little bigger than the ECC and the one RSA, and relatively new. So there is not much of a same binary means in the finite field or any other same field kind of an attacks also is not being reported. And also there is no same kind attacks using a quantum algorithm also not reported as of now. So we do not know really how secure, how long it is going to be secure. But however, relatively it is proved that it is relatively having a higher security than the known cryptographic attacks as well as quantum attacks. And the same way the crystal is used for the digital signature and Falcon is used for the digital signature, and the Sphinx, which is based on the hash-based algorithm, which is also based on the digital signatures. So details we can look at in the Google, like we can go through the standards and then we can get the details about this algorithm. So some of the informations that I collected from that is like, even though I'm working on this, but this kind of a things and all is like, as long as it is becoming a standard and it is NIST validated, mean to say that, yes, these algorithms and the details are being public. And nowadays, and even the moment it is published, I could get from some of the companies like say DigiCert and also APX and some other PKC, whoever is working on the digital certificates, right? They mentioned like, yes, we are all PQC compliant. That means to say that these algorithms are immediately being implemented, and then they are telling that yes, our particular product is PQC compliant. But thing is like these modules are not validated by NIST. I mean to say that what are the implementation approaches or the algorithms or the methods that have been proposed by them, it is need to be validated by either the third party or by NIST itself. NIST themselves, they do the validation by using a third party, whether whatever the proposed is, what kind of a methods we can use it, what are the modes that we can use it, and also what are the implementation parameters that we have to consider. So all the things need to be taken care. So even though the products are, they will say that it is compatible, but thing is like there will be a condition supply or the store they will put like depending on the module validation, because so far there is no report on this particular algorithm, this particular modes, whatever is mentioned here, whether it is proven reduction hardness or the key generation, encapsulation, decapsulation, and the other operations are on order of n squared, and then methodic transformation optimized for the speed, whatever may be the things that is being claimed here, it is not fully validated to commercial use. Yes, we can use it in the research purpose or we can use it in the labs and other things, but whether that is really being secure or not, that we have to wait for the results to use in the commercial. And also the currently known, or what I can say, currently known attacks or the algorithms which are used in any of these algorithms are Shor and Grover's algorithm, where Shor is about finding out the keys and Grover is about search algorithm, faster search algorithm. So these two quantum algorithms are applied on this crystal kyber, and then say that whether any other algorithm means it is resistant to some of the quantum algorithms. So far these two are the known algorithms, so that is why they implemented it. The same way if it is looking at the crystal, since it's a so it is also a signature algorithm, so just also looked at from the Grover's point of view, since there is no PQC or it is not used for the key exchange. So there is this is not a key exchange algorithm, so it is not looked at from the Shor's point of view, but it is looked at the Grover's point of view in the sense like what kind of collisions or what kind of attacks are possible on this. Same way when you are talking about the Falcon, and which is the PQC 2.205 is having two different algorithms for digital signature. One is a Falcon and another is a Sphinx. The Falcon is lattice based and Sphinx is a hash based. And there is a new hash function also being proposed, not a SHA-1, it is like a shape. So this also is on almost all the signature algorithms are tested against Grover's, but not on any other algorithm, because no other algorithms just been found for this. That is why we are means it is like known cryptographic algorithms. Either it is in the quantum side or it is in the classical side. They are validated against. So when you're migrating from current quantum system, current crypto system to quantum resistant crypto system, then we need to have a framework in terms of how we are going to prepare our organization wide, how they are going to prepare it. That means to say that we have to identify what kind of public key infrastructures, because as I mentioned, we are not going to look at the focus on the encryption side, because encryption is generally a symmetric key, data encryption side. But the key which is going to means moving around is based on the public key side. So what kind of a PKI is being used between what kind of systems, whether the organization is having between the computers, servers, IoTs, and also applications, and many things are there in that. So each of the things might be using the different, means we'll be using different types of PKIs among them. So identify what kind of PKI systems are there, and what kind of authenticated communication is happening between them, and what kind of a key exchange, symmetric key exchange to encrypt the data is happening between them. And also we have to find out what kind of tools we can use for migrations. So what are the effective standards, like whether the core business standards. For example, retail industry is a different standard, finance is a different standard, and manufacturing is a different standard, and medical is a different standard. So every industry is having their own standards when it is coming for the security wise or from the working in between the systems wise. So there are different standards are there, industry standards are there. What kind of standards are being affected because of this? And what are all the critical applications are being using this kind of using the cryptography or in this? What kind of protocols are there? What kind of authenticated communication is there? Again, we have to look at what kind of symmetric exchanges are there. And we have to define a process after that. Once we identify and then identify the tools for migration, identify the systems, identify the tools used to migrate, then we have to go for what is the process that we have to use in migration of from current cryptography to the post PQC. So what are the process? What are the protocols of negotiations that can be used? How we can invoke the crypto process? Well, how that currently being it is done, and how it will modify when you're doing that differently. Because when you are going for the PQC, the entropy kind of a things also will change. That means to say that currently most of the entropies are taken from either from the systems or from some of the true random number generated using HSM or some other things and all being used on this. So we also look at what kind of a crypto processor are being used, what kind of a crypto hardware and software and the processor are being used, what is the migration playbook. So we have to generate a playbook in terms of when you're migrating, what are the things that you have to look at it. And also we have to look at what are the technologies that are getting affected, how we can include those kind of things into the playbook. And then what are the standards? So once we arrive at this kind of a playbook and other things, whether we can standardize the migration process. Also, what are all the crypto modules are there, whether they are validated for crypto module validation program by NIST, that is CMVP, and what kind of informations are currently protected, how the crypto is impacted on the protected data. So we have to define a framework, and also what kind of supports are coming from the vendors. Suppose and if they are telling like currently when you are using some of these cryptographic standards, right? The implementation and other things, the support and all the things, they will say that okay, for next 10 years, 5 years, this is the life cycle on this. But when it is coming to PQC, it has been identified that by 2030 there is going to be a quantum computer will exist to break 224-bit of RSA keys. That has been predicted by Waterloo University professors. And by 2032, 1024-bit will be broken. So that means to say that what is the end of life of that particular PQCs or the protocols that they are defining on this? Because in 5 years, we do not know really what kind of what I can say, the attacks or what kind of evolutions can happen or what kind of algorithms can be defined. Because when it is coming to PQC, whatever to my knowledge and to my experience, whatever I have seen is, it is depending on what kind of algorithms that is being developed, whether it's in the research area or it is in the attacking on the cryptography in the sense like the Shor algorithms or any other algorithms. If you're looking at so these are all the things are being used with respect to attack on the current existing things. So though there are a lot of quantum-based encryption, one-time pads and the encryptions and the key exchanges and other things are there, but those things are based on quantum computers and quantum-based. So in one of the IBM researchers, when we are talking to them, he mentioned like if it is a 1000 qubit computer, effectively it is like 1:10. That means you mentioned like 1:10 or 1:100. That means to say that if it is 1000 qubit computer, after considering the error and all, it is like a 10 qubit kind of a computer. That's what I may be wrong, but I'm not really sure about it, what the numbers that he mentioned, but that is a little bit of like, even if you're having any number of qubits kind of a computers that we have, the error rates in the when it is coming for actually quantum measurements and quantum errors, when you're actually having the actual things that you are considering, it is probably about 1:10 or 1:50. I mean to say that for 50 qubits, one full qubit, that kind of a computer things that we will get it. So that is what the current statistics. It might improve. It will improve definitely. But thing is like, when we are going to have a first quantum computer on the desk or on the working area, that is when the crypto or the security related stuff, it will be rewritten. So thank you for your time and the patience. Yes. Yeah.
Thank you, sir, Muti, sir. So we have some questions in the chat box.
Okay. Just let me look at it. What does it mean for a cryptography protocol be quantum resistant or quantum safe? Okay, so quantum resistant in the sense like against quantum attacks, quantum algorithm attacks. Quantum safe in this, okay, quantum resistant and quantum safe. Mean to say that it is safe from, it is from the known algorithms, it is safe, it is resistant. Quantum safe in the sense, it is kind of what I can say. It is a synonyms, but exactly it is a kind of a synonyms. We cannot say quantum resistant in the sense like with the known quantum algorithms. Quantum safe in the sense also the same, more or less. It's not a protocol. Protocol will not say that quantum resistant or quantum, it's a cryptographic algorithms. Protocols is a set of rules. We cannot apply protocols to quantum resistant or quantum safe. You can say crypto algorithms, you can say whether it is a quantum resistant or quantum safe. Both are, it is like a synonyms kind of a things. If you look at from the output point of view. And data can be transmitted through logical channel in the classical data can be transformed to binary transformation. Yeah, that is right. That's right. I see only one question on this.
Okay, sir. Okay. Thank you, sir. Thank you very much, Muthu, sir. You
Yeah.
have one session.
Thanks a lot.
Thank you, sir. Thank you, sir.
Yeah.
Yeah, dear participants, tomorrow is the last day. We are on 6th day. So the session will be starts at 2 p.m. So we have 3 guests for the tomorrow session. So we'll start at 2 p.m. Dr. Rendraj Govindaraj, scientist at Experimental Quantum Physics Lab, Germany. And second session, Dr. Gururaj Kadri, scientific officer, Indira Gandhi Center for Atomic Research, Kalpakkam. And the third session, Dr. Satya Prakash Palniappan, IBM quantum educator. We have 3 sessions. The session will be starts at 2. After the sessions, we have a test and continue with the feedback link. We have validation program. So I hope we'll meet again tomorrow sharply at 2 p.m. Thank you very much. Good night.
No. Thank you, everyone.
Sir, thank you.
Bye.